That's so nice, Anna, that you have come all the way from Liverpool to visit us here in our solitary house in the forest and to listen to the old stories of your old teacher. And to begin with, let me treat you with something. I have to go and get it from the kitchen. Just a moment. Oh. Let me treat you to the mathematician's delight. I've bought a toy, magnetic sticks and balls with which you can make nice geometric constructions. Maybe when you go back to Liverpool you can take it as a present to Rachel. I don't know whether, would she play with such a thing? Sure. Okay, so I'll give it to you. And I've constructed the 5 Platonic solids. These are, that's not completely regular, that's unstable, you know that very well. So these are the 5 regular polyhedra. A polyhedron is a body in 3-dimensional space, compact, convex, and bounded by a finite number of hyperplanes. And these things have vertices and edges and faces. And let's look at them more closely. Let's begin here with the simplest one. That's the tetrahedron. It has 4 triangular faces. The next one is the octahedron. It has 8 triangular faces. And after that comes the most beautiful one. It's the icosahedron, which has 20 triangular faces. And then there are 2 other ones which are dual to these. Here is the the hexahedron, which everybody knows, but it is dual to the octahedron. If you take the 6 centers of its 6 faces, they are the vertices of the octahedron. And vice versa, if you take the 8 centers of the triangles of the octahedron, they are the vertices of the cube. These constructions were known from antiquity. In a similar way, the icosahedron is dual to the dodecahedron. These objects today are easy to describe. If you have the proper definition of what a regular polyhedron is, then it is an easy task to prove that there are only these 5 regular solids. But at the time when these things were discovered by the Greek mathematicians, it was a great discovery, and it had enormous importance for Greek philosophy. And to begin with, I think we should read a certain short sequence in a dialogue of Plato. The dialogue is called Timaeus. Timaeus was the name of one of the participants of the dialogue. At the point which I have in mind, they talk about the state of the elements, air, fire, water, earth, before the world was created in its present cosmic order by some demiurge, by some god. And let me now read to you, I have an English translation here in my German book, what he says. Before that time, in truth, all these things were in a state devoid of reason or measure, But when the work of setting in order this universe was being undertaken, fire and water and earth and air, although possessing some traces of their own nature, were yet so disposed as everything is likely to be in the absence of God. And inasmuch as this was their natural condition, God began by first making them out into shapes by means of forms and numbers, and that God constructed them so far as He could to be as fair and good as possible, whereas they had been otherwise. This, above all else, must always be postulated in our account. Note, Anna, that this is a confession of faith of Occidental science, or at least it has been its creed for 2000 years. Lately, I mean in the 19th century, some philosophers like Schopenhauer and Nietzsche began to have doubts about this creed. And for instance, Felix Hausdorff, on whose biography I'm working, once said, "Ich glaube nicht an Kosmos, Logos, Nomos als a priori feststehendes Ergebnis aller Wissenschaft, höchstens als glücklichenfalls Erreichbares." I try to translate, I don't believe in Kosmos, Logos, Nomos as a result of all science established a priori, but at best as something to be achieved if we are lucky. For Plato, the regular solids were the mathematical forms that represented the cosmological order. The tetrahedron represented fire, because it's so cute, the octahedron, the air, the cube, which is solid, the earth, and the icosahedron, water. Now, there were only 4 elements, but he had 5 polyhedra, so what to do with the last one? So it represented the cosmic order in its beauty as seen in the sky. Let me show you a picture, or rather a drawing, from the wonderful book Harmonice Mundi of Johannes Kepler. I love it. Here, on page 79, you see the 5 Platonic solids, and they are decorated so as to show the relation to Plato's theory of elements. Here's the tetrahedron, fire. Here's the octahedron, air. Here's the cube, earth. Here's the icosahedron, water. And then there's the 5th one representing the order and beauty of the cosmos to be seen in the sky. That's the dodecahedron. Isn't that beautiful? Kepler's book is a testimony for the fact that the Greek belief in cosmic nature of our world and the science of shapes and numbers, i.e. mathematics, is the means of recognizing this order. Kepler's book is a testimony to this fact that this is deep at the roots of Occidental science. Let's look again at Plato's Timaeus. At the point which I want to show you, they are talking about what is good for your body and for your mind. And then Plato says the following: all that is good is fair, and the fair is not void of due measure. Wherefore also the living creature that is to be fair must be symmetrical. Now, symmetry is of course a central notion of modern mathematics, but the Greek notion of symmetry must not be confused with it. What they meant is perhaps something like that the different parts of the body have to be in a harmonious proportion. There's no doubt that, for instance, fat people are not beautiful. But I think it's a question whether symmetry is a necessary criterion for beauty. Mathematicians have their notion of beauty. Artists may have a completely different notion of beauty, and human beings as individuals may have very personal and different opinions on what is beautiful. There was a time in our history where this Platonic notion of beauty as something regular was in high esteem. It was the time of the artist Dürer or the astronomer Kepler. At that time, regular polyhedra were all around in art. Let me show you one beautiful picture. It's an inlaid work which covers the lid of a precious chest which is now in a museum in Frankfurt. Mm-hmm. There you see an icosahedron here at left, a dodecahedron at right, another icosahedron here. There are also tetrahedra, there's a hexahedron, there's an octahedron, and then there are some Archimedean solids. Here's a 3-4-3-4, and here's a 3-5-3-5. It's a wonderful construction. It's a very precious work. Now, maybe if you look closely at it, you notice that the artist is playing a game which was popular at that time among the artists. They inscribed here in the pentagons of the dodecahedron smaller pentagons, where the vertices of the smaller pentagons are the midpoints of the edges. You can repeat this process. Do it again. Then you get 12 disjoint small pentagons, which have altogether 12 times 5, 60 vertices. Mm-hmm. And these points are the vertices of a very interesting convex polyhedron, which I'll call a golden 3-4-5-4. Let me explain why I call it like that. 3-4-5-4 means it would be an Archimedean solid, where at one vertex you have a triangle, a quadrangle, a pentagon, a quadrangle again. Mm-hmm. And they all have to be regular. Now this one does not have quite that regularity. The triangles and the pentagons are regular, but the quadrangles have a proportion of the edges like the golden section. That's why I call it golden 3-4-5-4. Mm-hmm. This polyhedron was made for me by an artist, Harry Müller, who lives in Leipzig. And I show you here the picture of what he did. Maybe you know it.
Is this the one in the library?
That was in the library, that's right. He worked for 1 year on it, and when it was ready, I donated it to the Mathematical Institute, and it was put up in the library. It has a wonderful property, namely you can inscribe in it 5 regular icosahedra. You see the edges made from gilded wire. I think it was a really beautiful thing, but when the Mathematical Institute moved to another building, it was destroyed. It was one of the saddest days in my life. Fortunately, not all works of art are destroyed so quickly. Here there are some which come from the Neolithicum. Mm-hmm. They were found in Scotland, stone balls made several thousand years before Plato discovered his regular polyhedra. And they have polyhedral symmetry. This has tetrahedral symmetry. This has a symmetry of the pentagon dodecahedron. And there are also some which have octahedral symmetry. Mm-hmm. Nobody knows why they were made or how they were made. You might conjecture that there's a mathematical theorem behind. In fact, there is a theorem here. If you want to arrange 12 points on a sphere such that the minimum of their mutual distances becomes a maximum, there's only one solution. The points will be the vertices of an icosahedron. Mm-hmm. but I doubt that this theorem was known in the Stone Age. Okay, that's what I wanted to tell you about symmetry in art. Plato postulated that any living creature which is beautiful must be regular. There are indeed creatures which are very, very regular. Let me show you a picture which I got from an Indian specialist for nanofossils. It shows a golden brown alga, that's a unicellular being, which is called Brachydosphaera bigelowi. It belongs to the coccolithophores. Coccolithophores are unicellular animals living in the ocean, part of the plankton, and they cover their body with a shell called cocosphere. That shell consists of coccoliths that are calcareous plates. Now this one here is a marvel of biomineralization. It shows an absolutely perfect pentagon dodecahedron, and each of the pentagonal faces consists of 5 trapezoidal coccoliths. Each coccolith consists of several layers of calcite crystals, microcrystals, all oriented in the same way. An unbelievable regularity. These coccolithophores have been around perhaps for 200 million years. They have completely transformed the Earth's geochemical system as far as carbon is concerned. You couldn't imagine life as it is today without these animals. To me, it's a great joy that this one, Brachydosphaera bigelowi, which was there at least from the late Jurassic period, is still alive. It still exists. Mm-hmm. Let me show you another picture. This is a drawing made by our colleague Hermann Karcher. Mm-hmm. Did you see it before?
No.
No? No. You see, it's a sphere decorated with a system of holes and walls which form hexagonal or pentagonal chambers. And there are 12 holes at the vertices of an icosahedron and 20 holes at the midpoints of an icosahedron. Mm-hmm. It's an absolutely perfect symmetry. Here you see the scheme of it. If you have one of the triangles of the tetrahedron, it's decorated like that with these walls and holes. Here you have holes at the vertices and you have a hole at the center.
So like around one hole, kind of a triangle.
Yeah, that's this is you can identify this with this, and here you have the faces. Mm-hmm. Okay, you know what it is?
Yeah.
It's the reconstruction of the pollen, how do you say in English? Pollen of a flower, pollen grain, yeah? The flower is called Cobea scandens, and I'll show you here now the pictures, 2 pictures. Here's the reconstruction. Here's the pollen of Cobea scandens. I got it from a Dutch paludologist, Wim Pant from Utrecht. I was there, I visited him and got many photographs of such pollen grains, and this is an absolutely perfectly beautiful thing. You see, it's the same thing. And here you see the plant. The plant is Cobea scandens. Cathedral bells is one name. The German word is Glockenrebe. I've grown it in my garden. What you see is a bat approaching the flower. The bat's name is Glossophaga soricina. That is a special kind of long-tongued bat. These bats visit flowers. It eats the pollen. Mm-hmm. It also eats insects. It also eats nectar of the flower. It eats everything. I mean, of these three things, but especially also the pollen. I got this picture from a scientist whom I revere, a late scientist, Professor Otto von Helversen. He spent many years of his life studying together with his wife bats and grasshoppers. They have very similar sounds, so it's difficult to distinguish them if you are not trained. Mm-hmm. And he investigated these bats which visit flowers. Von Helversen was a wonderful man and scientist because he, on one hand, knew all the modern mathematics, which is used to analyze, for instance, the echolocation calls of these bats. On the other hand, he loved these animals. Okay, so maybe you understand what I want to convey to you. How much have we understood of this whole story if we have seen the regular shape of the pollen? Now, to answer to this creed of Plato about regularity and beauty, I would like to read to you 2 sentences from Goethe. I've looked them up and my book is there, but I think I can quote them without the book. Goethe wrote, I will say it in German and then translate. Wenn ich also sage, dies Tier ist schön, so würde ich mich vergebens bemühen, diese Behauptung durch irgendeine Proportion von Zahl oder Maß beweisen zu wollen. So if I say this animal is beautiful, I would try in vain to prove this assertion by any proportion of number or measure. And at some other place, he says something which I believe is very true. He says, wäre die Natur in ihren leblosen Anfängen nicht so gründlich stereometrisch, wie wollte sie zuletzt zum unberechenbaren und unermesslichen Leben gelangen? If nature was not so thoroughly geometric in its inanimate beginnings, how could it finally arrive at incalculable and immeasurable life? I think that is very true. You see, with our modern methods of electron microscopic photography, in the small, an enormous amount of regularity. But if you look at living beings, if I look at you, I do not think of symmetry as a main property making you beautiful, right? Well, let's talk about symmetry in mathematics. In mathematics, the idea of symmetry is conceived in a very general way by the notion of group or of group of transformations. The creation of these notions is perhaps one of the most important developments in 19th century mathematics. From the Platonic solids, we get at once 3 finite groups. The groups of motions in Euclidean space transforming such a solid into itself. Let's look at the icosahedron. It has 6 5-fold axes. From that you get 6 times 4 rotations of order 5. So that is 24 rotations of order 5. Then you have the 3-fold axis given by the centers. There are 10 of them, and each of them gives 2 rotations of order 3, makes 20. Then you have the edges, there are 30, so that gives 15 2-fold axes, and each one gives a rotation of order 2.
to access through midpoints of opposite edges.
Exactly, yeah. So, and then you have the identity which doesn't do anything at all. If you add it up, 24 plus 20 plus 15 plus 1 is 60 transformations of the icosahedron. That's the icosahedral group. In the same way, you get the octahedral group of order 24 and the tetrahedral group of order 12. These are finite subgroups of the three-dimensional special orthogonal group. This three-dimensional Lie group is not simply connected. Its universal covering is the special unitary group, SU2, which can be identified with the group of unit quaternions which form a three-sphere. This three-sphere is the universal covering of the special orthogonal group, and you can consider the inverse images of these three groups which we have from the Platonic solids. Then you get groups of order twice the order of the groups. So you get the binary icosahedral group of order 120, the binary octahedral group of order 48, and the binary tetrahedral group of order 24. In addition to these, you have the cyclic subgroups of the special unitary group and the binary dihedral group. And that's all. Up to conjugation, these are the finite subgroups of SU2, and they will play an important role in what I want to tell you. There's another interesting class of finite groups that we shall have together to consider, which is generated in a completely different way. Namely, we consider groups of reflections in Euclidean space of any dimension. So reflections generate, you take reflecting hyperplanes and reflections, and then you want to consider finite groups generated by reflections. Now these were completely enumerated by Coxeter many years ago. The reflection hyperplanes decompose the Euclidean space into connectedness components which are called chambers. Take any such chamber and take the reflections. It's a simplicial cone, so its faces have the same as the number of dimensions of the space. Take the reflection in the walls of such a chamber. They generate the reflection group, and you can describe this reflection group by means of a graph, which is called Coxeter graph. Namely, associate to each of these finitely many reflections on the walls a point of a graph, and then the 2 points of the graph are connected by an edge if these reflections do not commute. And you get a weight for this edge, namely the order of the group generated by these two reflections. Yeah? That will be 3 or 4 or 5 and so on. If we have the order 3, I don't put this weight on the graph. It's understood that it is order 3. Otherwise, I put that weight on the graph. In this way, you can describe the group by this graph, and these graphs classify these groups. Coxeter made a complete list of them, and it can be shown on one page. It's graphs which you have probably seen, or some of them you have most certainly seen, but perhaps not all of them. Here is a complete list of the Coxeter graphs of the finite irreducible reflection groups. We will be interested only in those where all edges have the same weight 3. So these would be the cases AK, DK, E6, E7, and E8. Mm-hmm. There's some others are also they are all interesting. For instance, such reflection groups which leave a lattice in Euclidean space invariant, then this gives the crystallographic reflection groups. They would have to add this one, and here, and then there are some which are also very interesting where no such crystallographic condition is verified. And we will see that there is an amazing relation between these diagrams of type AK, DK, E6, E7, E8, and our groups obtained from the Platonic solids. Here I would perhaps like to make a personal remark. I met Coxeter first at the International Congress of Mathematicians in Vancouver. I had been asked there to present the work of Vladimir Arnold because Arnold was not allowed to leave the Soviet Union, so I had to do it. And Coxeter presided over the session where I presented Arnold's work. Arnold, I was, among other things, I had to talk about Arnold's work and his students' work on exceptional singularities, which you know very well. And some of his work was related to my previous work, and conversely, some of his work later stimulated work of my students, for instance, your work. Later, I got his classical book on regular polytopes, and I had it bound in a very nice binding, where on the front cover there's inlaid work showing the famous small stellated dodecahedron from San Marco in Venice. And then I sent this to Coxeter and asked him to write something for me into the book. And you can see here what he wrote. You see? Can you read it?
To Egbert Briscoe, with warm admiration from your old friend Donald Coxeter.
Of course, I like that very much, but old friend, I mean, old is true, friend is in some sense true, but I mean, we had only met briefly before, but we were close in spirit, I think. The next contact with him, the last one, was at the time when we wrote our joint paper, you and Rothenhäusler and me. That was, I think, in 2002. I sent a copy of this to him, because I thought he would like your figures. And he did not answer himself. His daughter answered for me and said that he was too weak to answer, but he had enjoyed it very much. And a few months later, she wrote me again, telling me that he had died, and that the things which we had sent him was something that made his last days easier. Perhaps I read from her letter. Dear Egbert, thank you for sending something pleasant for Dad to look at, even though too weak to write to you. But I want you to know he enjoyed it, which helped make those last days meaningful. For that I thank you, Susan. And I will show you a picture which was taken shortly before his death. This is Coxeter. I think you can see in what he believes. Nowadays, there are direct relations between the groups of symmetry of the Platonic solids on one hand and the finite reflection groups on the other hand. But historically speaking, the first connection, I think, came about by quotient singularities and by the work of Felix Klein. In 1884, Felix Klein published his book Vorlesungen über das Ikosaeder und die Auflösung der Gleichungen 5. Grades, Lectures on the Icosahedron. I have a copy of the first edition. I like old books, but I would like to show you here a new edition which was prepared by Peter Slodovy. This edition appeared in 1993, and Peter gave me a copy with a dedication which I like very much. See?
Einem treuen Verehrer des Icosaedes.
Peter Slodovy. Okay. So, to a faithful admirer of the icosahedron, Peter Slodowey. The binary polyhedral groups operate on the complex plane, hence also on its complex polynomial algebra, and Klein determined the ring of invariance and found that it can be generated by 3 elements with essentially one relation between these elements. This relation is an equation with the lowest term of order 2 in all cases. So these equations are given in the book here on page 63 and 64. And here you see, for instance, the relation for the icosahedral group, t squared plus h cubed minus 1728 times f to the 5th equals 0. Well, that's a subtlety, this 1728. Mostly we will have it in form t squared plus h cubed plus 5 to the 5th, f to the 5th. Okay? This equation appeared already a little earlier in 1872 in a paper of Hermann Amandus Schwarz. And Klein also got these equations earlier than the book which I showed you. Klein's result means, in modern terms, that the quotient of the complex plane divided by the binary polyhedral groups is an algebraic surface in complex 3 space, so it's a hypersurface, described by those equations. It has an isolated singularity of multiplicity 2 at the origin. Note that all these equations are quasi-homogeneous. Among other things, this implies that to study the affine surface or to study the its isolated singularity at the origin is nearly the same thing. So we shall mainly be concerned with these isolated singularities, which we consider as singularities of complex analytic spaces. Let's call these very special double points, which we get in this way from the Platonic solids, the quotient singularities for short. So we have dihedral, cyclic quotient singularities, dihedral quotient singularities, tetrahedral, octahedral, and icosahedral singularity. This terminology is perhaps not quite appropriate because you could consider more generally quotients by actions of finite subgroups of the full unitary group U2, and then you would get more quotient singularities, and I've described them in my paper Rational Singularities of Complex Surfaces, which appeared sometime in Inventiones. Okay, perhaps we should look at the simplest 2 equations of this kind. They come from the cyclic groups of order 2 and 3. And the simplest possible one is, of course, the one of order 2. So we have the equation x squared plus y squared plus z squared equals 0. I call that the A1 singularity because it corresponds to the Coxeter diagram of type A1. And the next simplest case is x cubed plus y squared plus z squared equals 0. I call that the A2 singularity. And then we shall also look at the equation later, x to the power 5 plus y cubed plus z squared equals 0. So that's the icosahedral singularity which we have just seen in Felix Klein's book. And that I will call, for reasons which will become clear, the E8 singularity. And we will use these examples to illustrate the general story which I'm going to tell. The first equation describes the simplest possible isolated singularity, namely an ordinary double point. It is a cone of a plane over a plane quadric curve, and you can resolve this singularity by replacing the singular point by this quadric curve. You get then a non-singular complex surface, and on it one exceptional curve which blows down to the singular point. this exceptional curve will be a non-singular rational curve of self-intersection number -2. So from the topological point of view, this curve is a two-sphere. And the surface itself can be seen as a normal bundle of that two-sphere, or co-normal bundle. I always get mixed up. You know perhaps better than me, I don't know. Anyhow, it's a line bundle over that curve. And if you want to have a small neighborhood of that exceptional curve, you can take a disk bundle in that line bundle. That will be, from the differentiable point of view, that will be a four-dimensional real differentiable manifold with boundary, a three-dimensional differentiable manifold. And we call this three-dimensional manifold a good neighborhood boundary of the singularity. In this way, we get a bridge from algebraic geometry or complex analysis to topology, to differential topology. And we shall look at other examples after we have developed some general notions about the topology of singularities. We've just resolved the isolated singularity of an ordinary double point, and this procedure can be generalized. If you take any complex surface singularity, isolated singularity, you can resolve it by a system of curves. These exceptional curves will be non-singular curves in a surface with negative self-intersection number, and then you can take tubular neighborhoods, and glue these tubular neighborhoods together, smooth the boundary, and then you get a four-dimensional, from the real point of view, four-dimensional manifold with three-dimensional boundary, and this boundary will be a good neighborhood of your singularity. The procedure can even further be generalized. If you have a higher dimensional isolated complex analytic singularity, you can again resolve it by a very general theorem of Hironaka, and then you get exceptional divisors of which may be very complicated, and you take tubular neighborhoods and glue them together, and the boundary will give you a nice neighborhood boundary of the singularity, which in that case may be much more difficult to calculate than in the surface case. So this is one way of getting good neighborhood singularities. There's another one, which is suggested by this picture. This is afterthought. I mean, I needed a long time to understand this. I will later tell you about this, how stupid I was. Consider again this ordinary double point, and then intersect it with a small ball. So the surface also intersects the sphere, the three-sphere, which is a boundary of that ball. And then you get a one-dimensional knot in that ball, which you consider also as a good neighborhood boundary. Or in general, if you have a two-dimensional surface, so complex dimension 2, real dimension 4, you will get a three-dimensional manifold, which is a boundary of that singularity. I'm jumping a bit with dimensions. So that would be, and that is also general. There is a theorem of Hassler-Whitney behind, which was, I think, proved in 1965. In general, if you take an isolated singularity, intersect it with a sufficiently small sphere, then the intersection with that sphere will be a good neighborhood boundary of the singularity, not depending up to diffeomorphism, not depending on the ball which you choose. So that is another way of associating a good neighborhood boundary differentiable manifold to the singularity. As a matter of fact, it agrees with the method which we have described before by resolution. Now there is an important variation on that procedure, and that was where I was so stupid because I didn't understand it for a while. Namely, you could first deform the given surface slightly. And if you make this, you first choose your ball sufficiently small, and then you choose a very small deformation. And that small deformation will again intersect the sphere in a nice manifold, which is diffeomorphic to the neighborhood boundary. So the big advantage is the following. If the deformed surface is smooth, you get a manifold with that boundary. And this manifold may be much more easy to calculate and to handle than the one obtained by resolution. So we have essentially two different ways of associating nice neighborhood boundaries to singularities. A, by resolution, B, by deformation. And it is a miracle somehow that for the singularities which come from the Platonic solids, there's a very close relation between these two methods. But I want to mention two other ways of looking at these neighborhood boundaries. One comes from the fact, which I mentioned before, that all these are double points. So you can describe the equation in the form z square equals f of xy. And then you can look at that as follows. You consider in the complex plane the curve with equation f of xy equals 0. And you look at your surface, at your complex surface, as a double covering of the complex plane ramified over the curve with this equation. And this was historically one of the first ways of looking at the topology of singularities. Around 1900, Wirtinger and Paul Hegardt looked at singularities of complex curves from this point of view. Yeah, you can do the same game and they found or complex surfaces. And if you do that, you find that for the simplest case here, the second simplest case, A2, that the intersection of this plane curve with this, so the curve has the equation x cubed plus y squared equals 0, the intersection is a trefoil knot. One could have, I think, a nice lecture on the cultural history of the trefoil knot, but that's another subject which we are not going to go into. So the neighborhood boundary of the A2 surface singularity is a double covering of the three-sphere ramified over the trefoil knot. And this is how they first looked at the topology of singularities in the beginning. And maybe that even goes back to Klein. Wirtinger was in close contact with Klein. Okay, this is one other way of looking at the neighborhood boundary of singularities. And then there is yet another way for this very special class of singularities, which we are considering the quotient singularities, because there these singularities are obtained as quotients of complex plane by the binary podahedral groups. So you can describe their neighborhood also as quotient of the three-sphere by the operation of this group. In other words, you have the SU2, which operates on itself by translations, and you have to consider that quotient, this quotient space. And this quotient space will then be a spherical space form. For instance, for the wonderful case of which we have here, the E8 case, you get the spherical dodecahedral space, because the three-sphere has this wonderful tessellation into 120 spherical dodecahedra, discovered essentially by Schläfli a long time ago. It comes from the four-dimensional regular polytope 533, which you can get as follows. You have these 120 elements of the binary icosahedral group. For each of them you have a tangent space, you have a tangent half space containing the origin, and the intersection is this wonderful four-dimensional polyhedron. And if you project these 120 pentagon dodecahedra to the sphere, you get the decomposition of the three-sphere in 120 spherical dodecahedra. And you can make a string of 10 of them if you consider a cyclic subgroup of order 10 of the binary icosahedral group. And then if you move along that string, then you see that moving from one to the next dodecahedron, this face is identified with this face by a twist of pi over 4, by a screw of pi over 5. If you would take 2 pi over 5, you would get the hyperbolic. Is it right what I say, or do I say nonsense? I think it is right. So you get this spherical dodecahedral space. And this I always considered as an extremely beautiful description of the neighborhood boundary of this singularity. And it is exactly the joy of this beauty which led me to ask Fisher to try to find a similar construction for the exceptional singularities of Arnold. And then it's also the same reason why I asked you to try to generalize this. I think it's extremely beautiful, and so this is a very specific way now of looking at wave neighborhood boundaries, whereas the other methods which I described are more or less general. Mm-hmm. But all have their merits and their rights. So there are essentially two ways of investigating the topology of singularities. One can do it by resolution or by deformation. And we will do that now for the quotient singularities and first look at their resolution. Now, resolving two-dimensional quotient singularities is in some sense easy, because they can be resolved by just blowing up isolated points. They are absolutely isolated singularities. There's an interesting story there behind, but work of Herzberg, which is before I started to work on the subject, but I can't go into that now. Anyhow, so if you have a two-dimensional quotient singularity, blow up some number of times the isolated point, and then you get a resolution, and in this resolution you will have a surface and in it an exceptional divisor consisting of non-singular rational curves with self-intersection number -2 and intersecting each other transversely in just at most one point. Once you know that much, you can say in advance which configurations of such exceptional curves you are going to get, because by a general theorem of Mumford and Grauert, such a configuration of exceptional curves on a surface can be blown down to a point if and only if the intersection matrix is negative definite. And this negative definiteness, together with the other conditions which I mentioned, gives you a possibility of enumerating the possible configurations. Such a configuration might be described by means of a graph, where to each exceptional curve corresponds a point, and to an intersection of two curves corresponds an edge between the points. This way of describing the configuration of exceptional curves, to my knowledge, goes perhaps back to Hirzebruch's thesis. Mm-hmm. And I think he got some of it from one of his two teachers, namely Heinz Hopf, who had, just before Hirzebruch became his student, he had introduced the notion of blowing up a point in a complex surface. Of course, that notion was known before in algebraic geometry, but Hopf applied it now in this context of complex surfaces. And when you blow up a point in a complex surface, that means you replace the point by a non-singular rational curve with self-intersection number -1. So that's, from the topological point of view, a two-sphere. And that's why Hopf called it a sigma process. Sigma is the first letter of the Greek word sphaira. So Hirzebruch learned this sigma process from Hopf, and Hopf had represented chains of such surfaces generated by such curves generated by sigma process, and called them sphere trees. And this word tree probably suggested to Hirzebruch to do that. And so he looked already at chains of such curves where all curves have negative self-intersection number, not necessarily 2, and investigated them. And if you have everywhere self-intersection number -2, these are exactly the resolutions of the cyclic quotient singularities. And what other configurations do you get because of this negative definiteness? Exactly those of type AK, DK, and E6, E7, E8, which I've shown to you before in Coxeter's classification of the reflection groups, or if you like, root systems for simple Lie groups where all roots have same length. And so you have these trees, you have this correspondence. Cyclic groups correspond to AK, binary dihedral to DK, E6 to the tetrahedron, E7 to the octahedron, and E8 to the icosahedron. And of course, my very favorite is the case of the icosahedron. There you can get a configuration of 8 curves intersecting each other exactly to the scheme of the E8 diagram, which I have shown to you before. And then if you want to look at its topology, you have to do the same thing as we did before in simple cases, namely take a tubular neighborhood of each of these exceptional curves and glue them together. This procedure had actually been used before by Mumford in an important article, I think, in David Mumford, published in 1961, where he called this procedure plumbing, a word which Hirzebruch then adopted. And that was a very interesting paper, also important for me. He calculated there from this intersection configuration the fundamental group of a neighborhood boundary, and proved that it is always non-trivial if you have a singular point, which implies then that a complex surface with an isolated singularity can never be a topological manifold. Yeah. He also looked in particular at this case of the icosahedral singularity with this famous equation that we are here seeing again and again, x to the power 5 plus y cubed plus z squared equals 0, and analyze that. Okay, for that you have this E8 diagram. Hirzebruch then lectured in Seminar Bourbaki. He reported there about Mumford's work. And at the end, he mentioned a construction of his own, which he had done which he had found in 1960. And I'm going to show you the paper to which he refers. It is the shortest paper he has ever written. It's in volume 1 of his collected works. I'm very fond of these collected works of Hirzebruch because he gave me these 2 volumes just when they appeared. And in fact, that was even before the whole collection appeared. This was one of the first volumes which he had in his hand. So I like this very much. And here you see this one-page paper zur Theorie der Mannigfaltigkeiten. He had presented that I think in Vienna. It appeared in 61, but he's done it in 60. And there he does exactly this plumbing procedure, but now not with two spheres, the rational in the surface case, you have two spheres for which you plumb tubular nebula, with spheres of any dimension. And if you take, for instance, a sphere of dimension 4, so then the disk bundle in the tangent bundle will have dimension 8. So you glue 8 copies of that according to this picture here. Yeah. And then he proves that the boundary of this is an exotic sphere of dimension 7 as constructed by Milnor. This is a very lovely construction. Milnor also liked it very much. He had done a much more complicated construction by such a plumbing procedure. But this direct relation to A8 was very, very beautiful. And at the end, you can see what he says there. Can you read it?
Die Konstruktion wurde motiviert durch die Singularität der affinen algebraischen Fläche Z1 zum Quadrat plus
Z2 squared, 2 to the power 3 plus Z3 to the power 5 equals 0.
In the point.
If you resolve it, then the singular point is blown up in an E8 tree of 8 non-singular rational curve of self-intersection number -2. So you understand why we had this model in the... Have you seen the model in the exhibition of models in the Mathematical Institute? In Bonn, in Weglerstraße? Yeah, it is there, or had been there since then. It was certainly made at Herzebuch's request. And I remember, I have heard this lecture. He lectured on it in our colloquium in 1960. At that time, I had not even got my diploma. Yeah, but I have the notes still today. I found it in the institute. I looked them up. I have made the notes. So since then, I knew that this fantastic construction of an exotic sphere, which originated from the icosahedron.
And this paper is half a page, is it?
Yeah, half a page. Fabulous. Now let's look at the other method of analyzing singularities, look at deformation of quotient singularities. The idea of studying an object by deforming it may appear to be natural, at least to mathematicians, although some variants, like studying an object, a human being, by torturing it, is perhaps less natural. Anyhow, in mathematics, these ideas occurred relatively early and frequently before a general theory of such deformations was developed. So first there are individual examples and ideas of this, and only later we have a theory. This was certainly so the case for the deformation of singularities, which I'll explain. We had a full-blown theory only around, I think, 1971, when Grauert proved the existence of semi-universal deformation for any isolated hypersurface singularity. However, there had been work which led to this result of Grauert by several other people, like Schlesinger and Kass and Thuriner. Let us simply look at some simple example. We will take, if we have the simplest singularity, A1, there is really nothing to deform, essentially. I've shown you a picture before. But look at the case A2, the A2 singularity, and let's first look at the corresponding plane curve. Here the equations are written Z2 squared minus Z1 cubed, so it's a cuspidal cubic in the plane. I show you real pictures, but one must essentially think of it as a complex picture. And then you can deform it just by adding an additional term to the equation, like here this linear term, and look at the level curves of this deformed equation. Then you get here such a rational cubic with a double point, and you have also other cubical curves which consist of two branches in the real case, and you see here one of these branches, such an oval.
other one goes.
Yeah, the other one goes there, right. And such ovals were studied very early. Namely, I will show you a page from the collected works of Euler, Leonhard Euler. Here, this is from his famous book, Introductio in Analysine Infinitorum, second volume. And here in chapter 12, he looks at Newton's theory of cubical curves and finds new aspects of it. Here you see such a cubic, similar to the one here. And then he makes the following remark about this oval here, this oval. He says, if you change the parameter, then this ovalis conjugata fiat infinita parva et abibit in punctum conjugatum. That is, the oval becomes infinitely small and disappears in this point. This is a singular point of this level, of this curve. And since then, or at least after this observation, these cycles are called vanishing cycles. I mean, I'm not sure whether historically this terminology really comes from Euler, but there is already this remark that such an oval gets smaller and smaller and shrinks to a singular point. Actually, as I said, in the real picture you see only half of the truth. Even if you consider only the curve case, we have to think of it as a complex analytic thing. So it happens in the complex plane, which is of real dimension 4. And unfortunately, our visualization in dimension 4 is rather defective. So I've made an extra effort in trying to visualize this. Nevertheless, I've drawn two real axes and one imaginary axis. And then you see that there are actually two such vanishing cycles on this level curve. This one and this one. Yeah? And one contracts to this singular point and the other one contracts to this singular point when you approach the singular levels. So, if you would now, for instance, in the curve case, but analogously you can say the same thing for the surface case, if you want to have a good neighborhood, what can you do? You can take such a disk bundle around these two vanishing cycles and glue them together, and you get again the same description of a good neighborhood of the singularity, but obtained in a totally different way, namely by deformation, not by resolution. In general, if you resolve singularities and get such a neighborhood around an exceptional curve, it's something totally different from what you get by this deformation procedure. But here, that makes you very suspicious. They are the same. I mean, topologically, not analytically, of course. Yeah? And here you see the diagram which describes the situation. Actually, this picture also occurred much earlier. It occurs at the beginnings of topology in papers of Listing and Möbius. Listing, you know, created the word topology. He was a student of Gauss. And Gauss and Möbius and Listing both have this construction in their papers. I forget exactly when, around 1856 or so. And there are conjectures that even Gauss may have known it. Yeah? So, here we have this plumbing procedure according to the A2 case, which leads to a good result. Let's look now again at our favorite and beloved icosahedral case. It goes exactly in the same style. Here you have again such a deformed curve like rational cubic, which we had. Now it's a quintic because you have a quintic equation. And I've drawn, you see that it has here 1, 2, 3, 4 double points. And then the level curves, the other level curves have more singular points here, 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 and here, which, depending on your choice of signs, may be maxima or minima. So you have subtle points here for the function and maxima or minima here. And so that you see if a suitable choice, a suitable deformation, gives you exactly the E8 diagram. This picture is a bit unrealistic in the sense that the true cubical curve which you would draw does not look like that. I have sort of forced it to go around this diagram. The true picture looks a bit different. And that you will see on a third picture, because there is a very beautiful variant of this construction, which was invented later after I had done my work by Norbert Acampo. I like that very much, and I must explain it to you. Namely, notice that all these equations which we have can be written with real coefficients. Yeah? So we look now at the real equations, z1 squared plus z2 cubed plus z3 to the fifth. And then you deform it really. You're only deform the equation taking real coefficients. So you have a function which you can see in the real two-plane. And suppose you've done it right, so that this function has only ordinary double points, which then will be either saddle points or maxima or minima, and it has a maximum possible number of double points. You can do that in various ways, and there's one way where the situation looks like in the picture which I show you. Here's this deformed curve. Yeah? Goes wildly around like that. Okay, but the additional idea of Acampo now is to look at the gradient field of this function. Yeah? And then the gradient field has a phase portrait where the special elements play a role. The maxima, the minima, and the stable and unstable manifolds which come from the saddle points. We look only at those stable or unstable manifolds which end up in one of the maxima or minima. And I've drawn them here. We have maximum, 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 maximum. And together with the saddle points, we have these 8 singular points. And the stable and unstable manifolds form exactly the E8 diagram. So the E8 shows itself without any mathematical effort, yet it appears itself like nothing. If you had an intelligent machine to integrate this differential equation, but they can't do it because they can't put the initial value exactly on the stable or unstable manifold. But if you had, it would be forced to draw this picture.
Right.
Okay, so I think that's extremely beautiful. But would you guess when this curve first appeared? What do you think? In the paper of Acampo? No, it was born in 1893. In 1893, in a paper of a female American mathematician, Charlotte Angus Scott. And I hold her in the highest esteem of having that seen, not with the E8 stuff. But she has found that this was a remarkable deformation of this cubic. And her method of deformation is not so different from what Acampo did. Isn't that interesting?
So what was her interest in this?
She studied algebraic curves in general and, so to speak, resolution and modifying them by rational transformations. Yeah, I mean the method consists in moving the curve over exoptional devices and blowing it down in another way, and so on. I can show you. She has written a whole book on it, and I can show you afterwards the book. Where unfortunately in the book she doesn't have this picture, but some similar pictures. Right. Yeah. Charlotte Angus Scott. My first love in mathematics was the theorem of Riemann-Roch. In my second undergraduate year in Munich, I took a course on sheaf theory by Helmut Röhrl, which was very tough for me because it was the second year. And at the end of it, he said if he would go on for another year, he could tell us about the theorem of Riemann-Roch. And I was deeply impressed of it. After all that hard work, we weren't even able to understand the theorem of Riemann-Roch. So when I finished that undergraduate part in Munich, I asked Stein where I should go to learn about the theorem of Riemann-Roch.
Right.
And then he said, you must go to Bonn, to Hirzebruch. So in summer term 1959 was my first semester in Bonn, and I enrolled in Hirzebruch's lecture on algebraic topology and also in his seminar on geometry and topology. And I remember the first day in his lecture, there was a very young man standing before the students. He was so young and he was also very different from the habits of German professors I had known before, that I thought it must be his assistant. But it wasn't his assistant, it was he himself. And I liked him from the beginning, and I wrote to my mother, he is very young and I have a lot of sympathy for him. So I became his student. And Hirzebruch had come to Bonn a bit earlier in 1956 after an offer of a chair in Göttingen had been withdrawn as a result of an intervention by Carl Ludwig Siegel, who had failed to recognize the importance of the new methods that Hirzebruch implied. So Hirzebruch came to Bonn. Hirzebruch had successfully applied these methods to prove the theorem of Riemann-Roch, and that was published in his habilitation thesis, Neue topologische Methoden in der algebraischen Geometrie, which appeared in 1956. This book, which culminates in the proof of Riemann-Roch, was for us an ideal textbook to learn about all these things. When Hirzebruch came to Bonn, he of course started to build a group of students, and both his lectures and his seminars were part of that. For me, I think the seminars were even more important than the lectures. I have always admired his wonderful and unique style of lecturing. It is so natural, and every idea comes just at the right moment, and as if it was generated in this moment. And this is particularly astonishing because if you've seen the manuscripts for which he prepared for his lectures, it was perhaps just a few formulas scribbled on a page or nothing at all. He claimed that frequently he has prepared the lectures during the 5-minute walk from his house to the institute. I remember one seminar talk where he explained the proof of the Riemann-Roch theorem, and all ideas were explained in such a simple and natural way that you had the feeling you could have proved it yourself. Okay. In these seminars of Hirzebruch, we learned a lot. We learned all the modern notions which we couldn't understand before about manifolds and fiber bundles and all kinds of structures, characteristic classes like Chern classes, and theories such as homotopy theory, obstruction theory, Morse theory, the index theorem. And also we learned the interplay of mathematical thought with these modern instruments and concrete, interesting problems and examples. This is very important, that you had not only theory, but many nice and beautiful examples. What the most exciting time of the year was always the Mathematische Arbeitstagung, which was created by Hirzebruch. There you had mathematicians of the first rank from the whole world coming together, talking about the latest new and fascinating ideas. And we, as students who could hardly understand all that, were sitting there and learning about that. That was really exciting. And it was, sometimes there were also additional lectures for us of the speakers. For instance, I remember Milner speaking on exotic spheres. And this was, of course, wonderful to have all these good people talking about the most fascinating mathematics. And of course, Hirzebruch students tried to make themselves acquainted with these new ideas. The first Arbeitstagung took place in 1957, and I should mention the names of the participants, because later some of them also I came to know them personally, and they have helped me. They were Michael Attila, perhaps the oldest and most faithful friend of Hirzebruch and of the Arbeitstagung, Michael Attila, Hans Grauert, Alexander Grothendieck, Friedrich Hirzebruch, of course, Nicolas Kuiper, and Jacques Titz. And then in subsequent years, other famous names were added to the list. I think the next year, Raoul Bott and Michael Kerver, John Milner, Jean-Armand Borel, and Serge Lang. And then in the 60s, in the late 60s, also some students of Hirzebruch had already the honor of presenting their results at the Arbeitstagung. I think the two first were my friend Klaus Jenich and Detlef Gromol, who spoke on exotic spheres and metrics of positive curvature. My own term came much later, when I had discovered the relation between singularities and exotic spheres. My own thesis, written in 1962, dealt with topics that were more in line with Hirzebruch's first work. I proved a theorem on complex quadrics, which was a generalization of a corresponding theorem on projective spaces proved by Hirzebruch and Kodaira. And I had obtained this theme because, as I said, I was in love with the theorem of Riemann-Roch, so it must be something with Riemann-Roch that I worked on. In the second part of the thesis, I dealt with objects which Hirzebruch had already considered in his thesis, namely the sigma n surfaces, that is P1 bundles over P1. And I generalized some of this to Pn bundles over P1 and looked at the deformation theory of them in the sense of Kodaira and Spencer. And after getting my PhD in '63, I became one of the 4 assistants of Hirzebruch. In the summer term, the first term was a summer term in '63, I had the feeling that I had to work too much for the Institute. And I remember that at the Arbeitstagung, one professor told me, you should not try to be a good assistant, you should try to be a good mathematician. So I say that to other people who are in that position. But sometime in September, I think, I started to work seriously on a new problem that Hirzebruch had given to me after finishing my PhD. And this was to generalize a certain result of Atiyah, published in 1958, I think, to all singularities which we get from the Platonic solids. It turned out that this was a wonderful idea, and I shall be grateful for it to my teacher till the day that I die. But I have to thank him for many, many other things. For instance, in the last years, he has helped us enormously in the edition of the work of Felix Hausdorff. Whenever we ran into difficulties, he has helped to solve the problems. And I revere him not only as my teacher and as a great mathematician, but as a man. He meets everybody with respect, with affection, and with care. And his friendly, open-minded, and sincere character has helped to make friends everywhere in the world, even in such countries which have suffered very much from the German crimes in the Second World War. At the end, I want to show you a photograph of him, which he gave me on the occasion, I think, of his 60th birthday. And I think that's very characteristic of him. He has also a very nice, dry sense of humor, and I simply like him. His birthday, by the way, is the same day as my father's birthday, October 17. so it's easy to remember. At some time in 1963, I asked my teacher for a problem for my first postdoctoral work. Hirzebruch gave me a 7-page paper by Atiyah, published in 1958 in the Proceedings of the Royal Society. The title was On Analytic Surfaces with Double Points. Hirzebruch suggested that I might try to generalize this from ordinary double points to all singularities of type AK, DK, E6, E7, E8. Atiyah's paper dealt with K3 surfaces. One of the results in his paper was that the famous Kummer surface with 16 double points, which you get by taking the quotient of a complex 2 torus by the involution, z goes to -1, that the minimal resolution of this Kummer surface is diffeomorphic to non-singular K3 surface, so in particular to non-singular quartic surfaces in projective 3 space. Well, once you've seen what I've showed you already, that the resolution and the deformation of an ordinary double point are topologically the same locally, it is not so surprising, this result. Also, André Weil says that he had noticed the same fact before. But Atiyah does more than that. He proves something different, namely, I will describe what he does. Suppose you have a family X is mapped to S of complex surfaces. So X is a non-singular 3-dimensional manifold, and S is a 1-dimensional non-singular complex manifold. And you assume that the general fiber is smooth, and you have one special fiber which has an ordinary double point. So that's the given situation. Now, you might wish to have a new family where the singular fiber is replaced by its minimal resolution, putting in one non-singular rational curve. But that cannot exist, because if you had such a family, it would be topologically locally trivial. And this is not possible because this family around the singular point will have monodromy. If you walk around the non-singular fiber, if you choose a path in the base space around the singular value and walk around, you will come back with a monodromy transformation. And in fact, that is non-trivial. It's non-trivial on the homological level even. It's a multiplication with -1 on the homological level. So it cannot exist. You must have some base extension. In fact, this problem will happen for all families, say, with quasi-homogeneous singularities. You can write down this monodromy even analytically, and from the weights you can calculate what the order of the monodromy is. And in particular, in the case of the AK, DK, and EK singularities, this number will be the Coxeter number. The Coxeter number, you recall, is the order of the product of the generators of such reflection groups which you get from a chamber. So, for instance, for the icosahedral singularity, the Coxeter number is 30. For the A1 singularity, it's 2. For the A2 singularity, it's 3, and so on. Okay, so what you want to have is you have here your given family X over S, and you want to make a base extension, say T to S, and then have a family over T, say Y. You want to have such a diagram that this is ramified covering, ramified over all singular values of this map. This here is a smooth map. All fibers are smooth. And if you restrict it to any fiber and map it to the corresponding fiber here, it's a resolution of the singularities. I will call such a thing a simultaneous resolution.
Where we think of S as parameter space.
Yes, S and T are the parameter spaces.
So simultaneous meaning will
simultaneous.
all
I mean,
parameters at
in the
same
beginning, in the beginning, like in the case of Atiyah, you had just a few fibers here which may have ordinary double points, and also in the beginning I considered S as one-dimensional, T as one-dimensional, but you can of course, and this was later done, you can generalize the notion. You take just any family here, and with of surfaces where maybe over many points you have singular fibers, if you have a higher dimensional base space, and then you have are looking for the same thing: ramified covering here, regular map here, and restricted to each fiber resolution, where we can leave open the question whether we want a minimal resolution or not. Okay. So that's this, this notion which perhaps I introduced, simultaneous resolution. It was then adopted by other people. Okay, that's what we would like to have. And Atiyah, in effect, constructs such a thing in the case of A1 singularities. It's an entirely local problem, so it's completely sufficient to look here at just one ordinary double point, given by an equation x1 squared plus x2 squared plus x3 squared equals something. So in general the map would be T, if this is S equal x1 squared plus x2 squared plus x3 squared, right? Now, in this case we are in the A1 case, so the Coxeter number is 2, so you would need at least a quadratic extension here of the base. So if that is a parameter here, you are led to the equation t squared equals x1 squared plus x2 squared plus x3 squared. Okay. So you have, if you have now done this, then you have lifted this family by means of this covering, and you have got a three-dimensional complex space with an ordinary double point now in dimension 3. Yeah. Now, if you would simply blow up the maximal ideal of that ordinary double point, that would mean to put in a complex quadric, because that's a cone, a two-dimensional complex quadric. And that would be the wrong thing. That couldn't give you a minimal resolution of the fiber. Couldn't give you any resolution of the fiber. So you have to do something better. But you remember that the complex two-dimensional quadric is a product P1 cross P1. Yeah? So you have two families of planes, planes in the space in which we are, such that every point on the quadric is contained in the corresponding line. So you have two families of lines. That's the whole story on this quadric. And so to every point, say x in three-dimensional, in four-dimensional space. We are in four-dimensional space, lying on that cone, quadric cone. There correspond two how shall I say, planes, P1x and P plus x and P minus x, planes of curves in this quadric. Yeah, and then you can make the construction that you consider the set of pairs of points x and p plus von x, p plus of x, and or minus x. And so you get two new spaces, and in this case then, of course, if you are not at the origin, you have only one such line, but the origin lies on all these things. So at the origin, you just put in one of these one-dimensional projective spaces. Yeah? And this is Atiyah's construction. It's just, I mean, going back to this very old idea that on a two-dimensional complex projective quadric is a product of P1 cross P1. Okay, so we have two different solutions of his problem. We have first lifted this family from here to here, get a singular point, and we have resolved it in two different ways just by putting in one of these two rational curves. Two solutions. Okay, so I took it at my task that this was my problem to generalize this. First remark is that I can write the equation of this cone also in this form, changing coordinates. Said I could write them at z1, z2 minus z3, z4 equals 0. Okay, that's a trivial modification. But this suggests what I did then. What did I do? That's already my next story. Okay, let's go on with simultaneous resolution. The construction of Atiyah gives the existence of such a simultaneous resolution for the maps X to S of 3 manifolds to 1 manifolds with only A1 type singularities. And as I said, I took it at my task to do that for all singularities of type AK, DK, EK. Now, when f of x, y, z equals 0 is the equation of one of these singularities as we've seen them in Klein's book, then this means that we make a base extension with of the form Td plus f of x, y, z equals 0, where d is hopefully the Coxeter number. Or maybe some other, we could try some other exponent, but the best chance would be, so to speak, the Coxeter number. Now, I tried, in particular, if we have singularities of type AK or E6 or E8, the form of this equation is particularly simple. It will be of this form: x to the power a plus y to the power b plus z to the power c plus t to the power d equals 0. Such a very simple form. And now I tried to find small modifications of such a three-dimensional singularity in a similar style as Atiyah was doing. Small modification means just putting in curves and not more to get these minimal resolutions. And one device which I used was to try to write this in the form, such a function in the form some polynomial phi1 times some polynomial phi2 minus phi3 times phi4 equals 0. Because then I got a map to the ordinary double point, and I could lift his curve and get in one curve. And I used several variants of this procedure. Instead of just mapping this can also be interpreted as looking at the graph of a meromorphic function, a meromorphic map to P1. Yeah, but I also looked at meromorphic maps to P1 cross P1 cross P1 to put in several projective curves at the same time. Anyhow, in this style, I managed to do all cases AK, DK, E6, and E7. And then started my misery because I was absolutely not able to do the E8 case. Later it turned out that when I had used this exponent 2, it was definitely impossible to do that, but at the moment this was not clear to me. So finally I decided to publish what I had, and this was a paper where these cases were solved and the one that remained. And during the Arbeitstagung 1965, I remember still very much the moment, I was talking to Hironaka about my difficulties with the icosahedral singularity. And he suggested that I should look at the process of modification as a process of blowing up ideals, and I must look at the divisor class group of the singularity. And this divisor class group for these singularities in question, these are three-dimensional isolated Cohen-Macaulay singularities, it injects into the second cohomology group of the neighborhood boundary. So I should first try to calculate the second cohomology group of the neighborhood boundary of such a singularity. That's what I did. Shortly afterwards, I set sail for New England because I had, following an advice for Firzebuch, I had obtained an MIT Moore instructorship, at MIT a Moore instructorship, and there that was an ideal place for me because at one hand in MIT there was Michael Artin, who had developed his theory of rational double points, which is very, very closely related to these quotient singularities. And I could always talk to Michael Artin, who was very, very friendly with me and a very, very nice friend, really. And on the other hand, in Harvard, there was David Mumford, who also had an interest on topology of singularities for a long time, and who was also very friendly and kind to me, and we could talk, and he gave me lots of good advice and discussions.
Who else was there? Who else was there who was kind of in a relevant area?
You mean in Harvard?
In MIT in Drumherum.
Well, in MIT there were several other people. I will mention one or two people afterwards, but for me, Michael Artin was by far the most interesting partner in discussions. And I had a roommate who was Tony Knapp, whom I didn't like. He explained to me why the United States must fight China and Vietnam. Whereas I, with Michael Artin and others, was demonstrating in New York against the Vietnam War. So there were people whom I liked and people whom I didn't like. Okay, but the more, so to speak, more important for me was perhaps, apart from the context with Michael, the contact with Harvard, because they had a wonderful seminar where there was Hartshorne, and there were several other people, algebraic geometers. One could even meet Oskar Zariski, and there was Raoul Bott. So that I had much from that. I mean, these are two different cultures, of course, as everybody knows. In MIT, the students were seeing movies like Pink Panther or such things, and in Harvard they were seeing old movies of Charlie Chaplin. So it's a really different world. Okay, let's come back to our singularities. Shortly after I arrived in Boston, I intended to calculate the divisor class group of this thing, say x squared plus y cubed plus z to the fifth plus t to the power 30, because that would be what the Coxeter number suggests, what I should do. But then Mumford thought this was too complicated, I should do something simpler. And so he suggested I do this, x squared plus y cubed plus z to the power 5 plus t squared equals 0. Now I know, but I didn't know at that time, that this is a unique factorization domain, so I couldn't find any divisor there to blow up. Okay, but even that for the moment seemed to me too difficult, so I did an even much more simple case, namely something like x squared plus y squared plus z squared plus t cubed. Yeah. And to my dismay, I found that this had no homology at all. I mean, in the groups in question, H2 and so. And it turned out that this thing was a topological manifold. Contrary to what I expected, because Mumford had proved for complex surfaces, you can't have a topological manifold when you have a singular point. But this was. I, in my stupidity, considered it as a negative result, instead of seeing that I had found something very interesting. After that, then I looked at, I think afterwards I looked at this case, but before I go on, I think I should mention that I visited, during my stay there, I visited Klaus Jänich, who was also in the United States, who was my friend.
So where was he?
I think he was at Cornell. And we had a very good time talking together in German, talking about German literature, and we felt a bit more at home there. I don't remember whether we also talked about his work, but if we did, certainly we didn't anticipate what happens next. In February '66, we got a letter from my teacher from Hirzebruch in Bonn, who had been following my work. Of course, I had told him that we had found this topological manifold, to our surprise. And on the other hand, he had also been following the work of Klaus Jänich. And in this letter, he told us on 8 pages that there was a very close relation between Jänich's work and my work, which we hadn't seen at all.
So he told you this from Germany?
Yes,
right?
Yes. I mean, it was all a frenzy exchange of letters then.
Wasn't emails yet? Yeah.
No, there was no email at that time. Namely, Jänich had been studying special G manifolds. You have a Lie group, think of a simple, for instance, a simple Lie group, which acts on a manifold, and you make certain assumptions about the structure of the orbits. Namely, it is you look at some point in the manifold, and then you look at its orbit under the action, and at the normal space to that orbit in that point, and the Lie group will act on that orbit space, and you want that it is, I think it is a trivial representation plus a faithful representation or something like that. And then one of the results of Jänich is that the quotient of the manifold by such a group action will be a manifold with boundary. Now, Hirzebruch noticed that more generally, if you take something like that, x1 squared plus xn squared plus, say, plus x0 to some power k equals 0. So that's a higher dimensional isolated singularity, quasi-homogeneous. And you intersect it with a sphere, so you add the equation x0 absolute value squared plus x1 absolute value squared plus xn absolute value squared equals 0. That there's an one, right, thank you. Then there is an obvious action of the orthogonal group ON on that. well, it's obvious to somebody like Hirzebruch. For instance, me, I didn't think of that. So, but for him. And it turns out that this is such a special, on this manifold, this is such a special manifold under this action. And in that case, the quotient space is a complex disk, where the interesting space happens on the boundary that's related to knots, but I'm not going into that. One might look at this as a kind of higher dimensional knot. And then Hirzebruch used Jenny's classification, and he used results of Bredon, I don't know how to pronounce the name, which had just appeared in topology, who had also worked on special manifolds with this orthogonal group and classified some of them, to find out that these things are for K odd, are homology spheres, except of course in the lowest dimension. Homology spheres, and moreover, in the case where n equals 5, so then this will be a 9-dimensional manifold described by this. It is an exotic sphere. And it is the exotic sphere constructed by Michael Cavere, gluing two copies of tangent disk bundles according to the A2 scheme. And I was so overwhelmed and enthusiastic about this discovery that I was completely outside myself, so to speak. And I wrote to Hirzebruch, I couldn't possibly imagine a more beautiful cooperation between the teacher and his students. And you have students because we were two of them. Okay. And then, of course, things started to get really very hot. I think the next step was that I now looked at this equation. Because, of course, we were speculating that, we knew that this has to do with E8. We knew that E8, this E8 construction of the exotic 7th sphere of which Hirzebruch had found. So this, the icosahedral singular, this thing coming from the icosahedron was certainly the most interesting object. And I resolved this damned thing, but this was quite a bit of work. I think there were about a dozen divisors which one had to plug in. This is complex dimension 3, so you have surfaces which you plug in with a complicated intersection configuration. But I did this work and calculated everything, and the result is this gives also, from the homological point of view, a sphere. And of course, then I wrote this to Hirzebruch also, and things got more boiling. And then something you asked, who else was in MIT? At that time, also John Nash was at MIT. You know perhaps that John Nash had become ill at some time, and sometimes in the evening, we were working late in the evening in MIT. I met him in these long corridors at MIT. He was, at that time, he had recovered to a certain extent and could talk mathematics. But for me, it was, in some sense, a terrifying experience. Because one had the feeling that, I had the feeling, as I wrote to my mother, because I found this depressing, that I had the feeling that here's an eagle with broken wings, a wonderful spirit who has lost his strength. But we were talking about these discoveries which were being made in singularities. And I will always be grateful for John Nash, what he did, because he must have gone to Princeton at some time and told Milner about these things. And a few weeks after we had got so far, Nash showed me a letter from John Milner. It started like that. Dear John, I enjoyed talking to you last week. The BRISCON example is fascinating. After staring at it a while, I think I know which manifolds of this type are spheres, but the statement is complicated and the proof doesn't exist yet. Let sigma P1 to Pn be the locus, and yet now comes this equation. Yeah? So perhaps we should rather, instead of P later, we wrote most of the time Z1 A1 plus Zn An equals 0, and also absolute value of Z equal 1. And then he gives conditions, relatively complicated conditions, divisibility conditions on these exponents A1 up to An, which are conditions so that this should be a topological sphere. And there was a little figure about 1 centimeter in size scribbled at the corner of the letter, which I must initially have overlooked, because of course I passed this immediately on to Hirzebruch in a letter and said I have no idea how he can prove such a theorem. And I will show you a much enlarged picture of his scribbled figure. It is here. Now you laugh because you recognize this, I suppose, but at that time I didn't recognize it at all. Perhaps I didn't even see it. It shows what we call today the Milner fibration. You take a small ball around the singularity, and you take an even smaller neighborhood of the singular value, take its inverse image in the ball. That's what Milner in his letter called a slab, but I don't know what an American word slab means. And this, and if you remove the singular fiber, you get a fibration. That's part of his way of looking at these things. And if you restrict it especially to a little circle around it, you have a bundle over the circle, where the general's fiber is a smooth manifold, complex manifold, and so you have a fiber bundle with monodromy. It's what we call today the Milner fibration, and the fibers are the Milner fibers. This later became an, how do you say, icon? How do you say in English? An icon for me. Almost all my lectures started with that, and not only mine, but also of many, many other people who worked on singularities. Of course, historically speaking, if you look back, and then you can see germs of that elsewhere. And what I told you before, I have suggested it. But at that time, it was really the new way of looking at it. Resolution was something everybody thought of, but this way of doing it by topology was definitely new. Okay, although I didn't understand at all what Milner meant, I was able to prove his conjectures, at least to a certain extent. And this was by sheer luck and complete accident, so to speak, because I was simply browsing on the bookshelf of MIT, and then I found an article by Frédéric Famm, in which you could see exactly those equations which Milner had in its letter. x1 to the power a1 plus xn to the power an. I think the title of his talk was something like Formule de Picard-Lefschetz généralisée, and something like that. So this goes really back to a famous treatise of Picard and Simard around the turn of from the 19th to the 20th century. I don't remember exactly the dates. And also to a famous treatise of Lefschetz, and Famm was doing this investigation because he was at that time working, I think, in Saclay, or at least somewhere elementary particles are investigated, and was interested in Feynman integrals and wanted to understand the properties of Feynman integrals. That was his motivation.
So was he was a physicist? Or?
No mathematician, but working with the physicists. Yeah, he was a Vietnamese, very kind and friendly Vietnamese mathematician living in France. So he effectively, what he did was exactly to calculate the middle homology of this, I mean, not only the homotopy type of this Milnor fiber and the monotomy. So I just had to use his calculations to prove that the statement about the homology which Milnor made. Of course, this got hotter and hotter. Bott in Harvard told me that I'm holding a lion's tail. I didn't understand that at the time. And I sent this to Hirzebruch, and Hirzebruch then found a nice way of calculating from Phams' result the signature for the middle homology of this fiber, which is the essential datum you have to know to decide whether your boundary is a sphere or not. Yeah, and in this way I could then characterize, I did the other case, I mean that is the 4 n-dimensional case, real 4 n-dimensional case. The 2 n-dimensional case, there you have the ARF invariant, which you have to calculate. I did that. And since Bott has told me that I'm holding a lion's tail, I hurried very much to write this down. In 4 weeks, I wrote a paper on that, which was called Examples for the Differential Topology of Singularities, and that was published in Inventiones, and that was really something which many people found exciting. And so in particular, one of the, that came then in particular, if you do that with these dimensions, so you have the sequence of numbers for these calculations. If you look at, if you look at this sphere, oh, I scribbled on that. Z1 squared plus Z2 squared plus Z3 squared plus, let me see, do I have enough squares? Z4 cubed plus Z5 to the power 5, 2, 2, 2, 3, 5 equals 0, and absolute value equal 1. This is complex dimension 4, so the neighborhood boundary will be of dimension 7, right? 2 times 4 minus 1, 7. And the result is you get the Milnor sphere, and you get, if you choose a proper basis here, you get the Milnor sphere obtained by plumbing of the E8 diagram. So finally we had exactly what we had hoped for and expected, that the neighborhood of this icosahedral singularity in this dimension is exactly the famous Milnor generator of the group of exotic 7 spheres. You have 28 exotic differentiable 7 spheres. There's one distinguished generator, this Milnor generator constructed by Hirzebruch in 1960 with a nice E8 constant. And here you have it coming from the icosahedral singularity. So we had a direct link between the icosahedron and the exotic sphere. Now that was interesting for many people, and there were many applications then of this. Namely, one could explicit the applications were mainly in the style you had already some general theory, but now you were able to construct nice simple examples. As the name exotic sphere suggests, it was considered as something exotic, something strange. But here you see it comes in completely naturally. It comes from the oldest objects that mathematics knows, these here. And in this way, some of the other applications were for all these exotic things, you could construct now fairly natural objects like equations for some combinatorial manifolds without differentiable structure, explicit construction of exotic differentiable and combinatorial projective spaces, explicit counterexamples to the Hauptvermutung. You see? The Hauptvermutung was such a natural conjecture, everybody thought it is true. And then Milner found counterexamples, and now there were even somehow natural counterexamples. Explicit constructions of exotic group actions, cyclic groups, S1 orthogonal groups. And constructions of metrics with positive Ricci curvature on exotic spheres. And then there was a perhaps minor contribution to which I self-contributed a little bit, construction of exotic examples of Hopf manifolds. That was an idea of my friend Van de Ven, and so he invited me and we wrote together a paper on that. But otherwise I did not take part so much in this kind of activity, because I was still obsessed with my E8 problem of simultaneous resolution of E8. I wanted to do that. This was, so to speak, an accident that this had been discovered, but I wanted to resolve the simultaneous resolution of E8. At times, I was so depressed that I couldn't solve the E8 case that I was nearly ready to give up. In the night, I was sitting in my apartment on Beacon Hill and looked at this icosahedron, which I had bought there, and tried to gather strength. But at that time, I just couldn't solve the problem. When the problem relating to these manifolds, sigma A0 up to AN, which Milner had posed, had been clarified by Hirzebruch, Milner and me in close cooperation and competition, sometime in May 1966, I returned to my old problem, and yet unsolved problem of constructing simultaneous resolution also for E8. And finally, in September that year, I was able to do it, and I found that the number of solutions of the problem, remember in A1 we had two different solutions, and in this case E8, the number of solutions is 2 to the power 14 times 3 to the power 5 times 5 to the power 2 times 7. You know what that number is? That's the order of the Weil group of E8. Order of the Weil group of the 8. And what does it mean? Local ring of this singularity x squared plus y cubed plus z to the power 5 plus t to the power 30. The second cohomology group identifies with the divisor class group, and it is of dimension 8 and has the structure of the root system of the lattice of weights of the root system E8. It is decomposed into Weil chambers, where the number of these Weil chambers is just this number which I gave to you. And each chamber corresponds to one solution of the problem. So that's the number of solutions. Namely, if you blow up any ideal in this Weil chamber, you will get a solution of the problem. But that's not the way how I proved it. That's an after-the-fact statement. The way how I proved it, I used very old work of Max Noether, I think, yes, on rational double planes. You have a double covering of the plane ramified over over a rational surface and I used properties on the configuration obtained by blowing up 8 points on on such rational surfaces. So very old stuff from Noether, and some of it I had learned from Hirzebruch and from Duval. So the problem was also solved. In some sense, I felt very satisfied. And then during the summer next year, in 1967, I returned from Boston to Bonn. And in October that year, October 17th that year, I dedicated my habilitation thesis to Professor Hirzebruch. It was just at his birthday that I finished it. And in addition to the results on quotient singularities, which I had obtained, and on simultaneous resolution, and on the relation between singularities and exotic spheres, there was also the germ of some new work in it, because in Boston I had got ideas from David Mumford, and I started to try to develop a theory of local Gauss-Manning connection for isolated singularities. The germs of that were already in my habilitation thesis, and that later developed in the next 2 years. I finished that work around 1969. While I was working on it, at some time I was in Oxford, and there I got very valuable ideas from Pierre Deligne and from Raghavan Narasimhan, which went into my proof of the monodromy theorem, which says that the monodromy around an isolated singularity of a hypersurface is quasi-unipotent. So the eigenvalues are roots of unity. This work then later stimulated work of several ones of my students, to begin with of Kyoichi Saito, which was perhaps the most important work going on, and then of Gerd Martin Greuel, and of John Shirk, and Wolfgang Ebeling, and the last one, Klaus Hertling, which you have witnessed yourself. But then in May 1969, Alexander Grothendieck read these papers of mine on simultaneous resolution. And he told me some very interesting conjectures on related problems. Up to that point, I had considered only these one-parameter families of surfaces and tried to resolve them. But he said I should look at the semi-universal deformation of such a singularity, and suggested I would find it in the adjoint quotient map of simple Lie groups of the corresponding type. That's a map which, roughly speaking, which associates to each element in the simple Lie group its semisimple part. The semisimple part would lie in some maximal torus, but the maximal torus is not uniquely defined. So the map really goes from the simple Lie group G to the quotient of the torus T by the Weil group W. So you would have a map from G to T divided by W. Okay? And he suggested that I should find the semi-universal deformation there, and I should also find a simultaneous resolution by looking at a construction that for the special unipotent fiber had been done by Springer, and which was then generalized by Grothendieck. This is then what was later perhaps called the Springer resolution. Yeah? And this goes like that. Here you have the mapping from the maximal torus to maximal torus divided by the Weil group. And this diagram is completed by constructing a certain space, let's call it, say, gamma. Yeah? And gamma is the set of pairs of an element G in the group and a Borel subgroup of the group with the property that G is an element in the Borel group. Yeah? Okay. Now, this is a basic setup. And then I could really, with the help of Jacques Titz and with the help of Grothendieck, prove his conjectures. First, I proved that there's now we have to look at this, say, at a unipotent element. So let G in this, or X in this particular case, G be unipotent. So that sits over the neutral element of T. And moreover, we want it subregular. The general element of G is regular, so there this mapping is smooth. And the subregular elements are the simplest singularities which this map can have over this fiber. Subregular means that the centralizer of this element has dimension equal rank of G plus 2. Okay, so look at such a point. And then, so we have then this mapping of germs from Gx to T over W at the origin. And with the help of Titz, I could prove that this has a factorization over some space X, and I will simply also write here X, which is not quite correct, where this is a regular projection, so the fibers are smooth, and this here is a universal unfolding of the Platonic singularity of the in question. So if you have an E8, the group belonging to E8, this Lie group, you would have the universal unfolding of the icosahedral E8 singularity. So there you have a description of the universal unfolding of the singularity in the group. As I said, Grothendieck said I would find it in the group. I could simply, so to speak here, make a section sending this to a transversal slice of the universal to the unipotent orbit, and then I would have identified it with a subspace of the group G, which is mapped by this map to here. Okay, that was part one. Part two was proved by Grothendieck, namely he proved that this diagram is a simultaneous resolution of the singularities of this map. Yeah? So in a much more general situation, you have every fiber here is a resolution of the singularities of the corresponding fiber here.
Right.
If you take that together, then identifying this with this, it means that you have finally a simultaneous resolution Y to T over your universal deformation T over W of the quotient singularity. You have simultaneously resolved the semi-universal deformation of the singularity. As a consequence, also you can say any deformation of one of the Platonic singularities has a simultaneous resolution. And only these have a simultaneous resolution also. So deformations of the Platonic singularities can be resolved had been found independently by Turiner, who, as you know, tragically died in an accident on a canoe. But we had exchanged letters before, so she also had the result, but not in this way, in this way. So here we had a very nice, beautiful connection now, direct connection between the Platonic solids on one hand and the quotient singularities and the simple Lie groups on the other hand. Whereas the previous connections were all with the diagram, with the Coxeter diagrams, here was directly an object showing the close relation between the two things. And then later there was a very nice I explained these results in a very short form at the International Congress in Nice in 1970, and I didn't write anything anymore about that. I mean, just a few pages proving it by brute calculation. And then there was a much nicer exposition by Peter Slodový, and not only exposition, he generalized it and applied it to the missing cases B, C, BN, CN, and so on. And he then wanted to extend some of this to the next layer of singularities, namely the simply elliptic singularities, which Kyoichi Saito had, so to speak, introduced in the field. And he's been looking at that for years and years and years. And then, Peter fell very ill. He got a cancer in his bones, and a terrible fight started for 10 years. But in the intervals when he could work, he worked on it, and shortly before his death, he found what he had been looking for all the years. I think that was a wonderful triumph. Oh, other interesting work then was also by Michael Artin, who characterized this universal solution of the universal deformation in a conceptual way, showing that these are two related problems of representation of certain functors.
When you say that one bit was kind of together with Tits, how did it happen? I mean, did you meet him and told him about what you were working on?
Well, for one thing, Tits was why I had been listening to lectures of Tits in Bonn. He lectured on Lie groups, and I was as a student, or maybe I don't know whether that at that time was already PhD. I had been in his lectures, but I didn't know much about Lie groups. And when Grothendieck came with these conjectures, I think at that time I was in Buer. And I had a chance to talk to Tits, who I think, I'm not sure whether he was at that time at the Collège de France. Anyhow, I was talking to him. And to me, it was surprising when I came with some of these problems and said, and here, for instance, there's this number or this number in my singularity story. He said, I will tell you the next number for your next example. Because he had so much the theory of Lie groups in his mind that he could, without any proof, predict results. And when I wanted to prove Grothendieck's result, as I say, I did this by brute calculation. I restricted this adjoint quotient map to such a slice, and now I wanted to prove that this restriction is the semi-universal deformation. And I did this by showing it's quasi-homogeneous and calculating the weights of this quasi-homogeneous map. Now it's a map, it's not just function, we have a map, a complete intersection map. And for that, you can do some of that work using special parabolic subgroups in the Lie group and all this kind of stuff, and the explanation of the Springer resolution. I learned that from Tits, how you calculate with that. So, as you see, they have almost all contributed to doing my work. No, I like Tits very much as a person, I must say. He was a very cultivated, very cultured person, very new, very literature. The colloquium at that time when Tits was responsible for the colloquium was something entirely different from what they have today there. That is all I say about that. Anna, you know that I'm really happy that you have come here. You know also that I have loved to teach you. I always like to teach, but I like to teach you particularly. And I've always also in my teaching tried to express the feelings which I have about the beauty of the mathematical objects. And for me, seeing was very important. And that's why I've been drawing so many hundreds and thousands of figures. You have some, I must say, I was a little bit sad. You made, you took notes of my lectures and everything, but the only thing that was not in the notes were my drawings.
It was a technological problem.
Yeah,
it was just
okay.
lack of
Yeah.
scanner.
Yeah.
Yes.
But I really made a big effort to develop also your geometric intuition. Although modern mathematics has become a science of structures, I am also fond of the old definition of mathematics as the science of numbers and figures. And figures, to me, are very much related not only to our possibility of analytical reasoning, but to our possibilities of perception, of seeing. So are, in a sense, more deeply rooted in our human existence, perhaps. When I was a child, at the end of Second World War, I was playing with ammunition. And as a consequence, my eye was hurt, one eye was hurt. And later on, in later years, for many years, I wasn't able to see with both eyes. I could only see with one eye. And when, by the art of some surgeon, I regained my eyesight, seeing in space, spatially, came to me as an ecstasy. And I can repeat that experience if I want, anytime. It's for me a marvel to see things in space.
So at which age was that?
What?
That was repaired?
Oh, I forget, but it was, you see, for some time it was all right. Then came long years where I couldn't see with both eyes, and then came the surgery, but I don't remember exactly when. Perhaps when I was 50 or so, I don't know. So I became really stereophile, if you understand what I mean. And so for me, seeing is very important. This was one of the reasons that I had to reflect also very much. I have reflected about space and time. The other reason was that I'm working on the biography of Hausdorff. And Hausdorff, who has created perhaps the most important general notion of space that we have, namely topological space, has thought for many years before he did his foundations of set-theoric topology, has thought with all of his emotions even, about space and time. And I've read a lot about what the philosophers write about the subject, but I'm convinced that space and time are miracles which we will never really understand. So, anyhow, this is for me very important to have spatial vision, spatial perception, spatial representation of our ideas. Hausdorff somehow has become part of my life in many situations. When some subject is being discussed, I imagine what he might have thought or said about it, and frequently it happens that we disagree on the subject. And I will give you two examples. One is about the role of Anschauung. I really don't know how to translate that into English. I mean, vision, perception, all that.
Visual perception.
Yeah, it does not really give the full meaning of what the German word Anschauung means. But you understand approximately what it means. And the other one, the other example about which I will talk afterwards, is perhaps altruism.
Mm-hmm.
There I also strongly disagreed with what he wrote and did and said. And about Anschauung, you know that this is a very delicate theme, because in the Nazi time, the Nazi ideologists claimed that the German soul has this special accession to Anschauung, whereas the Jewish analytical spirit hasn't. I mean, this was, of course, absolutely absurd nonsense, but it had bloody consequences. Hausdorff now had very clear statements about that. He wrote an important unpublished document entitled, I think, Formalism, where he states that the only reason to be sure about the truth of a mathematical theorem is truth and nothing is proof and nothing but proof. That's of course true. I agree completely with that. But I think almost any mathematician knows that this is not the way how theorems are found. They are discovered. I mean, many mathematicians have described the way how some ideas occurred to them, and it's a mysterious process in some sense. And I think the way how they are found is more deeply related with our whole existence than just the analytical thinking when we present a proof. So for me, Hausdorff, of course, admitted that Anschauung is very valuable and help also in finding theorems. And as I say, I admit completely that proving that only proof is a guarantee of a theorem, not an intuition. But if we teach mathematics, I think we have to try to convey something of the ideas and something about how we see and perceive mathematical objects. For me, as I say, Anschauung is very important. And that's also why I was so full of joy when Fischer found his polyhedron, which somehow generalizes the structure of the classical dodecahedron of the Platonic solid. It has a very similar kind of combinatorial structure, only that it has now a sevenfold symmetry axis as compared to the fivefold axis of the dodecahedron. And of course, the same reason I was so full of joy when you found your series of singularities, which continues this. At this time, I made a graphical work which I called my Opus 2. Yeah, I'm not an artist, but I just called it Opus 2, and you see it here. Have you seen that before?
Yeah.
Ah, yeah. I forget. Did I give you one to you?
I'm not sure which background it had.
Yeah, yeah. You mean there are other variants, but this is the one which I like most myself. It was made for the occasion of Hirzebruch's 75th birthday, because here you have 7 and 5. Mm-hmm. It contained, so to speak, to express my joy about this extension, because the Platonic solids are somehow something very finite, very limited, very beautiful, and it is beautiful that these finite objects occur in all different contexts. They are the simple singularities, they are the absolute isolated singularities, they are the rational double points, they relate to Lie groups, they relate to exotic spheres, but still there are just these 5. And now we had the beginning of a sequence. Here's the beginning, found by Fischer, and by you continued, so to speak, ascending to infinity. You may perhaps smile that I have such childish associations with that, but to me it was really a sort of ascending to sky, to the infinity. And so this is my feeling, which I made when I did this little picture. The joy for this discovery of new figures which are somehow nevertheless a continuation of this very, very old shape. But okay, This was one idea which I had when I made this. There's another idea which I will come back to later. Let me perhaps now come to the other issue where I disagreed so strongly with Hausdorff. That was even stronger, I must say, disagreement. He, as a young man, he had read the writings of Nietzsche, Schopenhauer too, of course, but then of Nietzsche. And he had adopted a position of Nietzsche which was developed as in contradiction to Schopenhauer. You know perhaps that Schopenhauer had preached a sort of universal compassion with other beings. And Nietzsche reacted. First, he found this wonderful, and for years he was quite filled with these ideas, with this Schopenhauer's pessimism. And then he tried to find an opposite position, exactly opposite position. And now he took the stance that what matters above all is your own person, that is at least a creative person, above all should tend to develop its own personality, its own creativity, its own creation, and should not care about others and not care about pity or something like that. And in this way, in the long run, with this egotistic attitude, would give the best he could give to society. Mm-hmm. I'm afraid that many people who have given mankind various precious gifts took that attitude. Anyhow, Hausdorff adopted it in this way, and said really some very unfriendly things about altruism, which hurt me directly because I feel I'm an altruist. And so I disagree very strongly.
But then what does it mean? I mean, was it his philosophical thinking, or was it what he implemented in his real life?
That's a very good question. Let me first say what he said and then answer what he was doing. He said that the highest ethical position he could think of was deep respect for oneself as a creative being, where creative is to be understood in a very general sense. It doesn't have to be things like writing books or something like that. Mm-hmm. Yeah, he had a very nice saying that who is creative, for instance, everybody who has something that is completely of its own. I mean, the pen name under which he wrote, Mongré, expresses the same thing. I want to do what is according to my taste. Taste is there used in the Nietzschean sense. So really, I mean, in a very short sentence, which struck me extremely in one sentence, but you must remember that was a young man who wrote that. He said, in short, what do I want? Myself. Mm-hmm. You see? Okay, that's one thing. Also, he said, if you are not altruistic, you would probably make less mistakes. If you think you are an altruist and want to help other people, you might make more mistakes than if you didn't, mm-hmm. because you don't know what they really think, what they really feel, what their real problem is, and so on. Mm-hmm. Now, if you ask how he behaved in his way, he was not like that all his life. He was extremely sensitive to other people, at least if they were in distress, tried to express his feelings I mean, for instance, when one Jewish woman was her husband had died and he was friends with his family, the Hausdorffs visited them And later she wrote to somebody else, Hausdorff's were here and were so soft and so kind and so on. So I mean, in this sense, he was not at all as the apparently brute person which he appeared. But there must have been a phase in his life where he really believed in this stance. And it is very tragic that at the end of his life, we have 1 or 2 letters which he wrote shortly before his death, when he and his wife killed themselves together. In these letters, other people who were writing to him were referring to his earlier adherence to Nietzsche's philosophy. And he said this, what Nietzsche said about the European development of Europe, where compassion or pity for pitying other peoples is a danger. That doesn't seem to be true at the moment. At least the historical event seems to be more or less proving the contrary. So he says, if I leave the positions of this philosopher, it may be so. So you see, there is, in my opinion, a very tragic way of seeing that maybe this philosophy was wrong. Anyhow, my own feeling about these things is really different. Also, and this relates, for instance, to me, mathematical creation is a wonderful thing and a great joy. I mean, I would never want to miss this experience which I have in my life. But it is not, to me, an absolute value. For me, in a very broad sense, love is much more. I think other people like Pascal have said that also very clearly. And so, for instance, love of my wife and living together and sharing things, sharing joy and sharing grief and working together every day is a deeper experience even than mathematical discovery. So if I had to make a simple choice between them, but life is not like that, I would vote for that and not for mathematics. Whereas Hausdorff has, as a young man, one must say, as a young man, very nasty sentences about the role of marriage and how you'd have to take care that your wife will take care of you. And also his daughter told me that her mother simply had the function to serve him. Yeah? Maybe that was one aspect which the daughter remembered. I think there will have been other aspects too. But
we're also talking about a very different time.
That's of course very true. I mean, you wouldn't believe what kind of nonsense people said about the topic Das Weib. Yeah, that is, I mean, you know that, yeah, at that time, that you're quite right. But somehow I think many people even today are sacrificing a lot of happiness for their mathematical work. Hausdorff himself at least quoted Nietzsche even much later, and in the sentence, why or what do I ask for happiness? I ask for my work. Yeah. So this is a point where I strongly disagree, and I think it is for the human existence, it's absolutely decisive that there's somebody else, not only me, but some you, some other being. And actually, my wife and I, we have extended this view. We cannot share everything. She cannot share my mathematics. She doesn't know how beautiful it is to share mathematical ideas. I cannot completely, although I love music, I cannot completely have the feeling that she has when she makes music together with other mathematicians. For instance, she had, with other musicians, but she has also made music, that's why I make the mistake, with David Eisenbud. Not that I'm jealous, but it's an experience which I cannot share. Yeah? So there are some things which we cannot share, but we do share a lot because we both love nature very much, and in a very broad sense. We have a deep feeling about life on Earth as a wonderful story that's going on for millions and millions, no, billions of years. I had a sabbatical at the IHS in Buer, and I found that the place had changed very much since my last stay in Buer, and I found it too noisy. So I simply left there and spent the sabbatical instead in a cottage in the forest, which belonged to my wife's mother. And there I worked on deformations of exceptional singularities while listening to the song of the pied flycatcher, which was singing at the entrance of my cottage. And after doing that for half a year, when I returned to Bonn, I was unable to live in a city anymore. So we started to look for a place where to live, and we found this house. And this house, together with land which we own, is not only our house, but also the house of the animals which we have here. You have seen some probably. There are squirrels, and there are dormice, and there are voles, and there are weasels and stoats and martens and foxes. All that is here, and we see them. And it's a great pleasure to watch these animals. And in summer, we can watch various kinds of bats, which are in the boxes that we have put up in the forest that belongs to us. They are fascinating animals. We watch them with a night vision glass, and with we listen to their echolocation calls in ultrasound. And I've shared that experience also with David Eisenbud, who visits us sometimes here. And it's these are simply fascinating animals. Our favorite one, I'll show you a picture of that, which I took just recently in August, I think. Look here, Anna. This is my favorite bat. Yeah, like that. These are the brown, long-eared bats. You see these long ears here?
So this is the view from below?
Yeah, I'm looking from below because it's hanging at the ceiling. We have created a place where they can stay in winter. Yeah, and they hang at the ceilings of that place. But to our surprise, they hang there also sometimes in summer. They are in winter there, but sometimes in summer too. See these fantastic ears. It's a very beautiful animal. Okay, there are about 5 or 6 of them. We can't figure out exactly how many. So it's a great pleasure. And we do a lot of work for the preservation of these bats. I'm not going to talk in detail about that, but that's one species for which we sacrifice a lot, let's say, of time and energy. And this is also something that, for me, is the kind of what I think of when I talk about altruism, because some of this work can be very frustrating. It is not so that this is some kind of hobby which makes only pleasure. Sometimes in nature preservation work is really very, very frustrating when you see what's being done to the species which you want to protect. The other species which we care for are just two very rare and exceptional kinds of butterflies, and I have a picture here too. These are the large blues, and there are two of them. This is a dusky large blue, and this is a scarce large blue. And they both depend entirely on one plant, that is the great burnet. And they also depend on certain very specific ants for their peculiar life. For that we also do a lot of work. And this common work done together is something that, so to speak, makes us both happy to have to do at least something for the preservation of these threatened species who have been on Earth long before the human species appeared. And here I come back to the second meaning which my picture has, this picture which I showed to you, my Opus 2. Because there is a second and less happy connotation with it. When I look at it, I also feel reminded of Swift's tale, A Voyage to Laputa. Have you read that? Maybe as a child?
Yeah.
We should read it. It's a satirical tale about mathematicians. Mm-hmm. They live on an island floating in the air. They care about only one thing, astronomy and mathematics. Mm-hmm. They care not in the least about all the absurd projects being pursued on Earth. And if I see that and look at this picture, then I remember that I think I told you that this series that does really not start here with the dodecahedron. It should start earlier at something with symmetry of order 3. Did I? Mm-hmm. I think I told you that. Huh? And this picture, this polyhedron, where it starts, that's on a famous etching of Dürer, which I had for a long time in my workshop, never really looking closely at it. And then suddenly when I looked at it, I said, aha, that's the beginning. And here it is, and here you see this polyhedron. And the title of it is Melancholia. Mm-hmm. And maybe you understand my feeling now when I look at these things.
To some extent.
A lot has been written about this. A lot of nonsense has been written about that. What I say is, of course, not in any way a historically reliable interpretation. It is just my personal feeling when I see these things together and think of Jonathan Swift and of our science and culture and civilization, which has made such a wonderful progress with the help of mathematics, but threatens to destroy the beauties that have been on this earth long before Plato started to write his Timaeus. See? So Maculinea Foundation, that's the foundation which Heidrun and I have founded to protect those butterflies. There you see two large blues, and they are on the plant on which they feed, which is called Great Burnet. There you see the meadow which we own and which we cultivate according to the life cycle of these butterflies. Yeah, you see I'm mowing there. There my wife is mowing also mowing, you see, Heidrun. We have tried to protect it by these signs. There we have planted this plant on which it depends uniquely, Great Burnet, yeah? It's a rosaceous plant, and they feed on that, they also mate on that, they lay also their eggs in it.
Without it, they can't live.
Yeah, and there I'm sort of monitoring it. We go along, we jot down the day, the sunshine, the temperature, and we count the butterflies. And then later these data are jotted down and analyzed. There you have this scarce large blue, that's even scarce large. And there you have mating, you see, of two of the dusky large blue. That's a dusky one. But this is not a burnet, this is something else. This is another plant, because there was not enough of the great burnet that year, so they also go to other ones, which of course they cannot lay their eggs on it. Here and I show you a sign which we are going to put up next to our meadows where our butterflies live. And here you see the life cycle. There are two species actually, the dusky large blue and the scarce large blue. And here's the dusky large blue. It comes out sometime in the beginning of July. It lives only for a few days, maybe between 3, 4, 5, 6 days. During that time, they must find a partner to mate. They mate most of the time on the flowers of the large burnet, and there they also put down their eggs. Here you see an electron microscopic picture of such an egg of a dusky large blue. The eggs have a beautiful structure. I can show you pictures of the structure of such eggs. From the eggs develop the larvae. Here you see the larvae, who also feed on the flowers of the great burnet. And at a certain stage, after some weeks, they fall to the ground, and then something strange happens. They have a certain pheromone which ants interpret so that the ants think it is a brood of ants, and they take the larvae and draw them into their nest. Here you see an ant of the species Myrmica rubra, which has here a larva, and they bring them into their nests. And there they stay during the fall, during the winter, and during the spring, and feed on the brood of the ants. That is, the dusky large blue feeds on the brood of the ants, whereas the scarce large blue is fed by the ants. There's also competition between this and this butterfly sometimes, so that both get into the same nest. And then it is difficult, because this one can only live with one species of ants, namely Myrmica rubra, but this one has several possibilities. He can use Myrmica rubra and Myrmica scabrinodes. So you see, it's a very complicated dynamical system there that's going on. At the end, the larvae pupate. Here you see pupa. And at this moment, they lose the protection by the pheromones, and then it gets dangerous for them. So they have to get out of the nest, and then the whole cycle starts again. Usually the Arbeitstagung began with a lecture where we could be sure that it was something interesting and exciting and important. Very frequently Michael Attila gave the first lecture. And then afterwards there was a program discussion where the program was determined for the next few days, and after that we would have another program discussion and so on. And during this program discussion, Hirzebruch stood at front and got proposals from the audience. In principle, everybody could make a proposal. And somehow, miraculously, at the end, the proposals were always those which survived and which were really then on the program, which were the most interesting and fascinating mathematics. And I don't know how Hirzebruch did it, but it was like that. I think that my mother did a lot to develop my mind so that when I was asking questions, they were answered. I mean, I think this is important when a child asks questions, not to say shut up, but to let its curiosity and interest in things unfold. So my mother has, for instance, told me that at some point, when I was a child, I don't know how old, maybe 4 or 5 years, I suddenly explained, now I know what electricity is. It is dried fire mass from stars. So in some sense, I see that very early in my life, I perhaps was interested in such questions. But the only other recollection which would perhaps go in this direction is that my father was an engineer, and an engineer who constructed mills for making meal. What is that? Meal?
Flour.
Flour, right. And sometimes I was sitting on his knees and he showed me the drawings of such mills with all the machines and so on. And my mother said, that's nonsense, this child doesn't understand anything of it. But apparently I liked it, and maybe my tendency to make such drawings has such a very early beginning, but I don't know. And when I was at high school, I was on one hand already interested in nature because we lived near a forest. And we were with my sister, I was many times in the forest and liked to be there. On the other hand, I had lots of technical interests, building radio stations and such things. So that's really not mathematics, but I had a good mathematics teacher in high school. And at some points, for instance, he tried to give me something that would go beyond the high school mathematics. And with some of these things he had success and with some not. For instance, he gave me a paper of Gauss and I didn't like it. On the other hand, he wrote something down for me, this description of a hyperboloid with its 2 families of lines on it. Yeah? And this I liked. And then we considered some interesting curves which were not usually looked at in school. And I enjoyed that and started to make my own curves too. I constructed some curves, things like the cardioid or something of this kind. I forgot exactly which. But otherwise, this was, so to speak, nothing exciting. Of course, I was the best student in mathematics in class, but when I had finished high school, it wasn't at all clear to me that I was going to be a mathematician. I intended to be an engineer for electrical engineering. But then I got this scholarship from this Protestant institution, which I mentioned, where we had to work for half a year in a factory. And the person who was in charge of all that was a man who apparently had a lot of understanding for the students which he had to care about. And he told me that I'm not the type of personality to become an electrical engineer. I should do something else, something more, so to speak, in the line of science. And so I decided to study physics. I wanted to be a physicist, and I studied physics in Munich. But then I suffered so much from the lack of clarity in their basic notions. I suffered terribly from their confused notion of a force, for instance. Maybe you have suffered from that too. And on the other hand, mathematics lectures were so clear and so elegant and so wonderful that very quickly I was completely converted to mathematics. This lecture of Röhrl was much of a challenge to me, and I think challenges, that's also something important. I have a completely different notion of how one should teach students from the absurdities which are now being done, where university is something like school, and you have first to do course A, and then course B, and then course C. I mean, that is, first of all, contrary to all German tradition, but it's also in itself an absurdity if you want to have creative students. So I think one should let students do whatever they want to do. Anyhow, I did what I wanted to do. So as a consequence, for a long time, I didn't learn any reasonable algebra until I had to lecture on algebra in MIT. Same thing with complex analysis, I think. I know approximately what a mathematician says when he says this or that mathematical object exists. But apart from that, I suppose most of the time when people say that something exists, they mean, at least I interpret it that way, they mean it is reasonable to behave as if such a thing existed. That is, existence is always an assumption which somebody makes that it is reasonable to consider or deal with certain kinds of objects or beings. I want to distinguish between these two. Yeah? When I say, for instance, that atoms exist, that was at Hausdorff's time. That was a question which was still in question, and one can see that in his writings, how gradually he shifts from the position that this is just a hypothesis to the assumption that they really exist. Yeah. When you say that such a thing, then I would say, yes, okay, the physicists have many good reasons to behave as if such things exist. It's confirmed. To work with that, you can prove lots of things. And you can go on like that with other elementary particles, and even those that haven't yet been shown to exist, which are just exist by theories anticipated. But there are the other words which where you use this word, like human existence, for instance. And that is much more complicated. What do you mean by that? That the philosophers have, of course, written a lot about that and distinguished between all the various modes. Existence, actually, these are very, if you look up in the historic dictionary of philosophical terms, you find that such words as existentia and essentia have very old roots in the antiquity, in the first centuries after Christ. And for instance, was a lot of debate whether these two notions can be separated from each other. Hausdorff did this on purpose. He separated the notion between, he said explicitly, I'm forcefully separating existence from essence, whereas other philosophers said you can't. Most people are completely naive about the use of such words as reality, existence, or whatnot. And in the course of my philosophical studies related to Hausdorff's works, I have lost all naivete. And I cannot give you a lecture on such things as existence or not existence, or truth, or even what you said, absolute truth, and so on. All that has, excuse me, for me, no meaning. Well, I've given you a sketch of the beginnings of some kind of mathematics, namely in Greek philosophy, in Greek history. There are, of course, quite different kinds of mathematics. My colleague Walter Purkert, who is a historian of mathematics, has pointed out to me that this is one conception of mathematics. And of course, there were others, like I think in China, in Asia, where mathematics was essentially very computational, where you proved, where you just give procedures for calculating something. It was a great achievement in some sense of Greek mathematics, to make such a conceptual presentation. And as I said, this then went through a long history. At the Renaissance, when Greek mathematics and Greek philosophy came back to Europe via the Arabs, Neoplatonistic views were infused very strongly, people like Galilei, people like Kepler. And so this was effective for a long time. And then, in my opinion, essential change took place around the turn from the 19th to the 20th century. Up to that point, there was mathematical objects, figures and so on, were considered in some sense as entities which have a character of their own. That was very much related to Aristotelic philosophy. What constitutes beings or things, what their essence is, and what the substance is, and what the form is. You see, these notions of form pervade all our thinking. They are very, very rooted deeply in the mental structure of human beings. And this changed at the end of the 19th century. And I think this change is related to one of the most basic changes in the history of mathematics at all, namely the introduction of set theory by Cantor. And then Hausdorff was perhaps the one who first brought this change into full force in his conception of mathematics, and which then later became even a kind of dogma in the mathematics as a science of structures. One German philosopher, Carl Friedrich von Weizsäcker, has said that the word structure is a modern equivalent, but it is not an equivalent, of the Greek idea, or of the Greek notion of shape, a form. The shapes which we see, we perceive them in an integrating way. if you show to a child one duck and another duck of another species and a third duck of another species, and you show him the fourth one, the child will say it's a duck. Without any notion of a duck, without any definition of a duck, it perceives a certain shape, a certain form, and knows these are ducks. The modern idea is to resolve all that into elements whose nature is completely irrelevant. They are simply called elements. Sometimes they are called points. Whereas in antiquity one considered points as non-existent. They didn't exist. This to the question about existence. And so they are resolved into elements, and between these elements are certain relations. The set of such a relation is called a structure. Almost any modern mathematical definition is of this type. Let X be a set of elements with this and this kind of additional sets of subsets or elements of the power set or something, and this is a structure which we call such and such. So everything is resolved. Imagine, for instance, your wife or your friend being resolved into a structure. And then you see, so to speak, what's being done. Now you think you put your hands onto everything. If you listen to the talk of politicians today, then every third word is structure. We have changed the structure, we make a structural reform, we change things this way, that way. You change even then the genetic structure of living beings. You change this and that and that and that and that. And mathematics, in some sense, has contributed to this. It increases the power of the human society enormously, but also the destructive power. So I have a completely ambivalent feeling about it. I've been now very outspoken. I didn't want to say that so explicitly. I want to send this message implicitly in what I told Anna.
I mean, it's not just mathematics, it's any kind of progress in science.
Yes.
That has this
Yes.
same effect.
Yes, but this notion of, that is true, but there is this common, science, if we talk about science, natural science, yeah, it is still, to some extent, this old belief that we understand the cosmic structure of the universe. First they believe that they know what the universe is, which is very ridiculous, yeah, and then they want to see its cosmic structure, creating chaos all the time, and then they believe that they can do that. But the belief has changed in its character. Say, let's take an example from another natural science. Take biology. Take, for instance, the work of Linné. Very patiently describing one flower after the other flower, one butterfly after the other butterfly, one tree after the other tree, especially using morphology, so the shape. So this is Greek somehow. We look at the shapes and the forms, and we see there's this form and this form and this form and this form. May it be mathematical or not mathematical. What you do now, A, B, B, A, C, D, A, B, C, D, A, B, C, C, A, B, D. And then you have Monsanto, who tells us how to change it. And really, there are now many botanists, I know that, or zoologists at the universities, who cannot distinguish even simple species of animals and flowers from each other. I know them, I know personally. Old people who knew that. I know a professor here in Bonn whom you could show any flower in Germany and he bets that you will not be able to find one which he doesn't know. There are about 3,000 or 4,000 of them, and at least I have never been able to show him a flower which he didn't know immediately. And he tells me that his young colleagues, which are successors of these old people, are not able to distinguish even very common flowers. Or another example, which has direct relation to our work in nature protection. These butterflies rely on certain ants. And you have to know before you start such a project, before you want, for instance, to buy land where they could live, to know whether these ants are there. For that, you have to look through a microscope and determine which ants are there. It's a very acute work. You have to look at smallest difficulties, differences in the shape of these ants. I know a woman who has written her thesis on that and who's doing this work for me. I've paid her for that. Okay? And then I have a book, for instance, for determining these ants. I don't want to do this painful work myself, and you have to have a lot of experience. But I have a book written by somebody who is an expert on that. And he says in the introduction, I thank the museum where I work to be able to have it made it possible that I write this book, because at the university this would not anymore be possible. But what these people do then at the universities, they analyze the DNA of lots of ants and try to solve some problems. For instance, which ant separated from which ant so many million years ago, or which ant in Norway somehow is deviating slightly from another ant in Finland or so. Okay? And these people are even sometimes not able to distinguish the ants which they analyze, so that the results get wrong, even wrong. And I think this indicates this change in attitude. You don't take the living being anymore as an entity in its own right. You consider it just as a system, and a system which you can describe by a sequence of letters, or many sequences of letters. I have a colleague, Andreas Dress, who has made the mathematics for them. I've had very fierce discussions about this once with one of my colleagues, because he said the only criterion which you can apply to a mathematical result, whether it's true or not, or whether it's beautiful or not, he meant beautiful. Whether it's good in some sense, because you see, for the Greek mathematicians, good and beautiful were together. Yeah. Now, the only question is whether it's true or not, and that is done by proof. So, but it is just this complete remoteness from anything else which increases the power of human mind enormously. If you want to kill somebody, I mean, you don't, but maybe you have a bad dream and kill somebody. If you are in such a situation, if you have to do it with your hands directly, it's terrible, you can't do it. If you are far away, just push a button. Maybe you can do it. There are enough psychological experiments which show that. The pilots which throw their bombs onto people, they have just a screen on which they see. It's a pattern which you can practice somewhere. And this is not only my idea. I mean, the ethical implications are mine. But for instance, Poincaré has said, just if you remove far and farther away from this apparent reality, this increases the power of the human mind. So, unfortunately, Hausdorff is right. There is no other way of deciding whether a theorem is true, and whether a theorem is important, and whether some mathematics is important or beautiful. That's decided by the consensus of the mathematicians of good rank or high rank in general. This means if I want to do this pure mathematics, as long as I know it is pure, as long as I do not know of some dangerous or bad application, I can do it, but it is not enough for me to do nothing but that. Then I should, in some other field, live up to my obligation as a human being, which is a member of the human community and has other obligations. That could be social obligations, that could be cultural obligations. For me, it is preservation of nature, but also peace. I've been very active in the peace movement. Yeah, so I should do something like that. At least I feel this is a way to at least live with this ambivalence of this Janus face of science in general and mathematics in particular.
When you said that you think mathematics shouldn't be the only thing in the life of a mathematician.
For me.
Other things
For
you, other
yeah.
things important as well. At the time when you worked on the
Yeah.
exotic spheres,
Yes.
was it the same?
Not quite, but to a certain extent. For instance, at that time I told you that the Vietnam War was going on, and we were demonstrating in New York. There was a big demonstration where Martin Luther King was speaking, and I was glad that Michael Artin and other colleagues from MIT came with us, I went with them to New York to go to that demonstration. And on the other hand, I must say, it made me sad that when the Iraq War started, that there was so little protest from American mathematicians. Whereas here, I and my wife, we have demonstrated against the Iraq War at Frankfurt, near some airport. And we were carried away by the police, but we told the police that we do everything together, even demonstrating, so they should bring us together afterwards, which they did. No, even at that time, I thought, it is of course true, you are right, at that time the mathematics was the much overriding issue, but not completely. I was at that time also found, like many people, recreation in nature. And then afterwards, when I had returned and I was a professor in Göttingen, I was, for instance, involved in aid to Cuba, scientific aid, sending them the experts they were asking for, sending, for instance, somebody who was an expert on breeding cows or so, or guiding some ophthalmologist, physicians from Cuba around in Göttingen and so on. So I think this, I gave you this example where I was in this Protestant organization supporting students. And we had a saying which was a kind of joke which we made, but which I really somehow realized in my life. The name of this institution was Felix. That was a little village where this institution was located. Mm-hmm. And we called ourselves Felixter. And the saying was in German, ein Felixter tut ein Übriges. That was in some sense self-ironical, but on the other hand, it was also our conviction. So how do you translate it into English? A Felixter does the things which are not, which he must not necessarily do. Yeah.
Goes beyond.
Those beyond that what you can demand. How did it come about that I got so much involved with Hausdorff? There were I think two basic moments which triggered that. One was that his daughter was living in an Altersheim. What is that?
Old people's home.
Old people's home. She was already had to be in bed all time. No, at that time she wasn't. He was not yet. But our students wanted to put up in the Mathematical Institute a stone plate commemorating Hausdorff. And at that time I was politically perhaps more sympathetic with revolutionary students than with my conservative colleagues. And so there was a debate about what should be written on this plate, on this marble. You know that is in the entrance of the Mathematical Institute. And we wanted to have a sentence in it like, nie wieder Gewaltherrschaft, nie wieder Krieg. Yeah? Never more again dictatorship, never more again war. And we found that very good, but some colleagues were against it. And then Hirzebruch said, but what could you have against this sentence? And it was finished, so it was decided that we have that. And my wife and me, we organized a bazaar to collect the money. We sold lots of things to collect the money for the thing, and so it was there. The other board commemorating Toeplitz was done by Hildebrand alone, essentially. So that was one thing. At this occasion, when it was put up on the wall, Hirzebruch's daughter was invited and was there. And then later when she... Hausdorff's daughter, yes. And then later when she was in this asylum or whatnot, I visited her sometimes there and listened to what she told me. So I felt then a certain obligation. The second was that at some point people pointed out this is the 50th anniversary of Hausdorff's death. And people from outside our university, because we hadn't been thinking about it, from some other university, told us we must do something. So we got together and said what should be done. We must make perhaps an exhibition of some of his works, some photography, and such a thing. And then arose the question, who is going to say something about his biography? Silence. And then I said, okay, then I'll do it. This is this example of to do something that others don't want to do. And then my colleague, one of my colleagues, whom I like very much, is a nice person, said, oh, then we have solved the most difficult problem. Yeah, but this solution for me has lasted about 20 years of my life. Yeah, because then we got into the edition of the works, and I have really made a lot of sacrifices to get this thing going. So this is all about this doing something that is not directly mathematical. Of course, it is somehow related to mathematics, but as I mean in this biography, the other people are doing the mathematics, and I'm very grateful for that way. I mean, it's a group of 24 mathematicians, historians of mathematics, historians of science, people working in philosophy and literature, German literature. So it's a very big task, and that's on a completely different scale, I feel. Yeah? And in some sense, much more complicated, and sometimes also much more frustrating. Because, and in particular, exactly for somebody like Hausdorff, who wanted so much to be an individual on its own, not as Nietzsche said, ein Herdentier, yeah? Mon gré, à mon gré. He wants to live as he wants to be one. And then you see that this being cannot live like that, because at some point in the Weimar Republic, when you have these mass demonstrations and you have these the Nazi time coming up, he notices it is not anymore the time of the individual. The masses now are on the street, and the new gods are there, Volk, Reich und Führer. And at the end, he says in his letter before he takes away his life, man hat uns nicht leben lassen, da man uns nicht leben lassen will, wie wir wollen, we found another solution. So this relation between an individual and the society in which it lives and the times in which it lives is a very, very complicated and difficult matter to describe. And it's, so to speak, so much more complicated than the most difficult mathematics in some sense. On the other hand, the mathematics requires a much better mind than my mind to understand all that.
When you say that the mathematics now is all structures, not shapes and stuff, I mean, the feeling I have is when mathematicians actually think about mathematics, they don't really think necessarily in terms of structures, they still think in terms of some shapes.
Probably.
Which might not be concrete shapes like this, but they still have, I think the human kind of thinking process works with shapes and some pictures, some visual information, even if somebody thinks about very abstract kind of of structures. And I mean, some of the things you worked on were not as explicit and concrete as polytopes, but what kind of what kind of images did you have? If you think about a manifold, 7-dimensional manifold, and
that's an interesting example. For instance, I think whenever we speak about something, in principle, everything we have seen, heard, or lived in our whole existence might come into play. So if mathematician A talks to mathematician B and says, let X be a Riemannian manifold, then B may have a completely different notion in his mind of what a Riemannian manifold is from what A has. Maybe one has seen hundreds of interesting Riemannian manifolds of a certain kind of type, maybe hyperbolic ones or Lorentzian ones, and B has knows just the definition and or has some general notion of connections on manifolds and so on. They can discuss with each other because the mathematical language is so controlled that they will agree about all assertions as to truth. But what is in their mind may be very different, and if there's a good understanding between them, there might be a sharing of ideas. Now it comes to my mind a letter which I got from Hélène Hénault. You know her? Yeah? And she explained to me that for her, this sharing of ideas with other mathematicians is the most important thing in her life. And so she talks to many, many, many mathematicians and wants this kind of togetherness in understanding ideas. And just because there's this difference in the minds, one has this notion, you cannot say notion, you has the word manifold in his mind creates a certain resonance. And for the other one, there's another resonance with other overtones and other deep undertones. And if this is a good communication, then there may be a resonance between the two of them. And that is something beautiful. That is something very beautiful. And that is just makes it interesting. If we had all the same notion of something we are talking about, it would be very boring. But on the other hand, we have been conditioned by our training as mathematicians in the first year. Yeah, mathematicians, students are conditioned. I've always been astonished when I have a student in examination and I ask him a certain mathematical question. The mathematics students, the good mathematical students, usually will answer right on the spot, immediately. So and so and so and so. And how is this possible? Because it is quite certain that they have another or completely different experience from mine in mathematics. But for the minimal amount of communication that is necessary to state the logical truth, this conditioning is enough. Mm-hmm. And on the other hand, for a deeper understanding, this getting together in a discussion that is something extremely personal, and I wouldn't be able to say what I have and to say in any few words what I have in mind when I say a manifold. Mm. You see, when we, as I told you, when we were students in Hirzebruch seminars, we learned all these modern notions. I had some of that in Munich as a student. For instance, one of our teachers, who was a more old-fashioned mathematician, explained to us the notion of a differential form. I was completely unable to understand what he meant by that. Then I come to Bonn, I learned what the fiber bundle is, what the tangent bundle is, what the alternating products of bundles are, and that a differential form is a section in one, and okay, it's clear. Yeah, you see this conceptual work, of course, so if I say manifold, I have this in my mind. But if I say manifold, I have also in the manifold in my mind, somewhere in the back, and it might come up, is a dodecahedral spherical space. Yeah, or the manifolds which I've shown in these pictures. Mm. And I have more in the mind. I have in mind the history of the notion. When Riemann created the notion of a manifold, how does he start? Did you read his famous paper on that? I mean, the hypotheses which are at the basic of geometry, or something like that. It's a very famous paper. Did you read it? Mm-hmm. Okay, so you know what he says, talking about a manifold. There are few examples, apart from mathematics, which we are going to develop, where the notion plays a role. One example, he says, is colors. Mm-hmm. Yeah? And you have this infinite family of shades and, of different colors. And this is a very good example. And also I have in my mind I like, as I say, with things which have to do with vision. And I studied a little bit about vision of colors, perception of colors. There are very interesting experiments when you show students colors and ask them to identify a certain color. For a physics student, it's no problem whatsoever. It's that color, it's that. He gives you the name. If you have a student of art, he has a much longer reaction time. Because when he sees this color, he thinks of a certain painting of such and such from the 13th century or so. Mm-hmm. So what does he have in mind? Well, when I say manifold, I have these things also in my mind. Yeah, and then I have in mind that manifold was a beautiful word in German Romantic literature. Mannigfaltig is a beautiful word in German. I mean, it has a beautiful sound. It shows you rich variety of things. So what do I have in mind when I say manifold? And the longer you are, fortunately when one gets old, one forgets many of the things which one has learned, otherwise the brain might be overloaded. But this is, I think this is was a very well chosen example to show we don't really know what is becomes active in a given moment depends so much on your disposition, on your feeling, on what you have at the moment access to.
But probably in the communication between mathematicians who work together, the formal definition is just about the last thing on the list of these things, which is important for their conversation. I mean, it becomes important when they write things up.
It is good to have that. I mean, on the other hand, the formal definition is important, because I think I said that before, that I think the creation of the notion of group was one of the central inventions of 19th century mathematicians, and I think the other central notion to me was exactly the notion of manifold. And I think it is a great, great development that in the 20th century we have really unfolded this notion, because there are topological manifolds and differentiable manifolds, and then there are also analytic manifolds, and there are combinatorial manifolds. And we see that all these notions are different. To a large extent, first they thought that it is all essentially the same, but each notion is different, and it's a wonderful achievement of the mathematics in the 20th century that we've sorted that out. So personally, when I think about manifolds, most of the time I will probably think of differentiable manifolds or complex analytic manifolds. But if we, for instance, talk about applications of the little discoveries which I made, then we certainly also thought about topological manifolds which are not differentiable. And so it really depends. In some sense, the precise definitions are important, and in some other sense, not. It depends. Let me take a completely different, since you said that what we have in mind may be different from what we are showing on paper. I once was in Michael Artin's office in MIT, I think, and he was thinking about some problem. I don't know which problem it was, but he did not draw any picture or something like that. What he was doing, and for a long time, he was drawing an arrow and drawing an arrow and drawing an arrow and drawing an arrow and drawing an arrow. And you can see that very probably the problem he had must have been a problem which from a statement in category theory, because from these areas. But what? That is completely different, unclear. Yeah. At the time when I was doing my PhD, I was assistant in Erlangen, and there were some other friends who were approximately at the same age. And at that time we were somehow making jokes about category theory. Nowadays we have colleagues in the institute where category is every third word, categorization. On the other hand, I think it's a great achievement, approximately perhaps or nearly the same size as set theory. On the other hand, there is a paradoxical element in it. Namely, the basic notion is that of a morphism. But where does the word come from? From the Greek word morphe, which is gestalt, shape. And instead, they are using that word all the time to describe structures. There are no shapes there. I mean, morphism is something that preserves to some extent shape, structure. And but as I say, here shape is always interpreted as structure. So that's not the Greek notion of morphe, of gestalt. Yeah? Your gestalt, your body, your physical body, and also the shape of your mind, that is something entirely different from a structure, to me at least. Yeah. Okay, so what did Atin think when he drew all his arrows? What did he have in his mind? I don't know. Our mind is something very, very mysterious.